Have you ever witnessed the wonders of modern engineering, where human ingenuity and construction come together to create structures that change what's possible? Join us as we explore the world of extreme mega projects, revealing the most impressive and groundbreaking megastructures of today. From cutting-edge stadiums to colossal bridges and more, this documentary highlights the impossible achievements that are transforming the planet.
It's time to talk about the ATU Dam project, located on the borders between Brazil and Paraguay. This colossal structure harnesses the power of the Parana River, generating a staggering 14,000 megawatts of electricity. The dam plays a vital role in the energy supply of both countries, providing approximately 15% of Brazil's electricity needs and 75% of Paraguay's. Construction of the ATU Dam began in 1975 and was completed in 1984, involving a massive workforce and significant engineering challenges. The dam itself is about 4.8 miles long and 643 feet high, creating a reservoir that covers an area of 521 square miles. The reservoir, known as the ATU Reservoir, has a total storage capacity of 29 billion cubic meters of water. One of the most impressive aspects of the ATU Dam is its power generation capability. The dam houses 20 generating units, each with a generating capacity of 700 megawatts. These units utilize Kaplan turbines, which are highly efficient for the varying water flow rates of the Parana River. The power generated is transmitted through high-voltage lines to both Brazil and Paraguay, playing a crucial role in the economic and industrial development of the region. Environmental and social considerations were critical and integral to the project. The construction of the dam necessitated the relocation of around 40,000 people and significant ecological changes, including the creation of the ATU Biological Reserve to protect wildlife. The project also involved extensive reforestation efforts and the establishment of fish hatcheries to mitigate the environmental impact. Managed jointly by Brazil and Paraguay through the ATU binational entity, it stands as a testament of what can be achieved through collaboration.
Let's talk about the incredible Braa Bridge, which is located in Romania. This bridge, spanning the Danube River, connects the regions of Moldova and Dobroja and is a testament to the innovative engineering solutions. Costing $600 million to construct, this bridge was awarded in 2017 to a consortium led by the Italian construction company WeBuild and Japan's IHI Infrastructure Systems. The construction officially began in December 2018 and involved over 1,350 workers, showcasing the massive scale of the operation. One of the most impressive features of the Braa Bridge is its main span, which stretches 1,120 meters. This makes it the second longest suspension bridge in mainland Europe. The bridge's total length is 1,974 meters, and it includes two imposing towers that raise to a height of 192 meters. These towers are not only structural marvels, but also the tallest structures in Romania. The construction process was highly intricate and involved several critical phases. The bridge deck comprised 86 segments, each weighing approximately 260 tons. These segments were fabricated by Fincantieri in Italy and transported to the construction site via barges. Once at the site, a specialized lifting beam was used to hoist the segments into place, a process that required precise coordination and engineering expertise. The bridge's suspension cables are another engineering marvel. Made from over 18,000 steel wires, the total length of these cables stretches 81,000 kilometers, which is enough to circle the Earth twice. These cables weigh a combined 6,775 tons and are crucial for supporting the bridge deck. The installation of these cables involves intricate techniques to ensure their stability and durability. Building the bridge's foundations posed significant challenges due to the region's soft clay soil and medium-high seismic activity. Advanced techniques such as extensive piling and deep well excavations were employed to ensure the stability of the foundations. Piles within a diameter of 1.8 meters were driven to a depth of up to 45 meters to provide a solid base for the towers. The bridge is designed to withstand extreme conditions, including winds up to 270 kilometers per hour and substantial seismic tremors. This resilience is achieved through meticulous engineering and the use of high-quality materials. The bridge's deck is suspended approximately 40 meters above the river, allowing for the passage of medium-sized ships. A significant engineering feat was the installation of the two main suspension cables. These cables were assembled from thousands of individual steel wires, meticulously intertwined to form robust support structures. The process of anchoring these cables to the towers required precision and advanced engineering techniques to ensure their strength and longevity.
We move over to Seattle next, where the Alaskan Way Viaduct Replacement Tunnel project stands. This project replaced the aging and seismically vulnerable Alaskan Way Viaduct with a 1.7-mile-long double-deck highway tunnel running beneath downtown Seattle. The tunnel is part of a State Route 99 and was constructed to improve safety, reduce congestion, and enhance the city's waterfront area. The tunnel's construction utilized a tunnel boring machine named Bertha, which was, at the time, the largest of its kind in the world, with a diameter of 57.5 feet. Bertha's journey began in July 2013, but the project faced significant challenges soon after. In December 2013, the TBM came to an unexpected halt after encountering a steel pipe, which damaged the machine's cutting blades. This led to a prolonged repair period that lasted nearly 2 years. The TBM was eventually repaired by excavating a recovery shaft from which engineers accessed and lifted the front of the machine to replace the damaged parts. The tunnel boring process resumed in December 2015, and Bertha continued to carve its way beneath Seattle at an average depth of about 200 feet below the surface. The tunnel was constructed using a segmented ring system, where each ring is made up of 10 precast concrete segments. As Bertha moved forward, these segments were installed to form the tunnel's lining, providing structural support and preventing groundwater ingress. To ensure the tunnel's long-term durability and safety, engineers used a comprehensive monitoring system to track Bertha's progress and the surrounding ground conditions in real time. This system included sensors embedded in this tunnel's lining and the ground above, allowing for immediate detection of any movement or settlement that could indicate potential issues. One of the complex aspects of the construction was managing the groundwater and ensuring the tunnel remained watertight. The tunnel passes through the Duwamish River's alluvial deposits, which are prone to high groundwater pressure. To address this, Bertha was equipped with a pressurized front shield that balanced the pressure at the tunnel face, preventing water from flooding the excavation chamber. The final breakthrough occurred in April 2017, marking the completion of Bertha's journey. However, the project was far from over, as extensive work was required to outfit the tunnel with necessary infrastructure, including roadways, ventilation systems, fire suppression systems, and emergency egress routes. The tunnel officially opened to traffic in February 2019, replacing the viaduct and transforming Seattle's waterfront. But what about the International Thermonuclear Experimental Reactor project located in France? Located in Saint Paul Metro, this international project involves 35 countries and has an estimated cost of around $25 billion. Construction of the project began in 2010, with the project entering the assembly phase in 2020. The reactor is designed to produce 500 megawatts of fusion power from an input of just 50 megawatts, achieving a 10-fold energy gain, which would be groundbreaking of a milestone in fusion technology. The primary construction challenge is the sheer scale and complexity of the reactor components, many of which are being manufactured and assembled for the first time. The core of the project is the tokamak, a donut-shaped vacuum chamber where the fusion reaction occurs. The tokamak must withstand extreme conditions, including temperatures up to 150 million degrees Celsius, 10 times hotter than the core of the sun. This requires using superconducting magnets to create powerful magnetic fields that confine the hot plasma within the chamber, preventing it from contacting the walls. The construction of these superconducting magnets is a major engineering feat. Each magnet, known as a toroidal field coil, weighs around 360 tons and comprises several kilometers of superconducting cable. These cables are made from a special alloy that becomes superconducting at very low temperatures, maintained by cooling systems using liquid helium. The project also involves constructing numerous supporting facilities, including cryogenic plants, cooling towers, and electrical substations. These facilities are essential for maintaining the reactor's operation and ensuring the safety and stability of the fusion process. One of the key innovations in the project is the use of remote handling systems for maintenance and repairs. Given the extreme conditions inside the tokamak, human access is impossible, necessitating the development of robotic systems capable of performing complex tasks with high precision. These systems are designed to operate in the harsh environment of the reactor, handling radioactive materials and high temperatures. Rail Baltica is a major infrastructure project aimed at integrating the Baltic states into the European rail network. This project involves constructing a new high-speed rail line connecting Estonia, Latvia, and Lithuania with Poland and the rest of Europe. The construction of Rail Baltica includes building new tracks, stations, and supporting infrastructure. Building the new tracks involves extensive earthworks, including excavation, grading, and laying ballast. The tracks are constructed using continuous welded rail, which provides a smoother and more reliable surface for high-speed trains. Engineers use advanced surveying and alignment techniques to ensure the tracks are straight and level, essential for maintaining high speeds and safety. The construction of stations and supporting infrastructure involves creating passenger facilities, platforms, and maintenance yards. These facilities are designed to be modern and accessible, providing a high level of comfort and convenience for passengers. Additionally, the project includes the installation of advanced signaling and communication systems to ensure safe and efficient train operations. One of the significant challenges of Rail Baltica is coordinating construction across multiple countries, each with its own regulations and standards. Engineers and planners must work closely with government authorities and stakeholders in each country to ensure the project meets all requirements and progresses smoothly. Furthermore, the project incorporates numerous sustainability features, such as energy-efficient systems, green infrastructure, and noise reduction measures. These elements reduce the environmental impact of the rail line and enhance the quality of life for communities along the route. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency.
Next up, we have to move to Germany for an incredible stadium project called the Allianz Arena. Located in Munich, this project is a modern architectural marvel and one of the most advanced football stadiums in the world. Constructed between 2002 and 2005, it was designed by the Swiss architects Herzog and de Meuron, with structural engineering handled by Arup. The stadium serves as home ground for both Bayern Munich and TSV 1860 Munich, with a seating capacity of 75,000. The construction of the Allianz Arena required extensive planning and innovative engineering solutions. One of the most striking features of the stadium is its exterior, made up of 2,874 diamond-shaped panels. These panels can be illuminated in various colors, allowing the stadium to change its appearance depending on which team is playing or the type of event being hosted. The material is not only lightweight, but also self-cleaning and resistant to adverse weather conditions, making it an ideal choice for the stadium's facade. The structural frame of the Allianz Arena is composed of reinforced concrete for the bowl and stands, while the roof consists of a steel latticework covered by the panels. The design of the roof and its support ensures that all spectators have an unobstructed view of the field. The upper tier of seating is inclined at 34 degrees, which optimizes sightliness and enhances the spectator experience. During the construction phase, approximately 120,000 cubic meters of concrete and 22,000 tons of steel were used. The precision required for the construction of the stadium's roof was particularly notable. Each panel had to be accurately positioned to ensure proper alignment and lighting effects. The panels are pressurized to maintain their shape and structural integrity, providing both thermal insulation and acoustic dampening. One of the key engineering achievements of the Allianz Arena is its lighting system. Originally using conventional fluorescent lighting, the system was upgraded to a fully digital LED setup provided by Philips. This upgrade involved installing over 5,000 meters of network cable and more than 250 LED lights, which significantly improve energy efficiency and reduced maintenance costs. The LED lights are capable of displaying 16 million colors and can create dynamic lighting effects which are controlled via a sophisticated digital platform. The Allianz Arena interior is designed to cater to a wide range of needs, including hospitality, business, and fan services. It features 2,152 seats, 106 VIP boxes, and extensive facilities such as restaurants, bars, shops, and conference rooms. The stadium also houses a large media area, daycare center, and fan shops, making it a multifunctional venue beyond football matches. Additionally, the Allianz Arena boasts Europe's largest underground car park, capable of accommodating nearly 10,000 vehicles. This massive parking facility was a crucial component of the stadium's design, ensuring easy access for the large number of visitors on match days. It's time to move over to the Yavuz Sultan Selim Bridge in Turkey. Completed in 2016, it's a remarkable feat of modern engineering that spans the Bosphorus Strait, linking Europe and Asia. This bridge, with a main span of 4,619 feet, is one of the longest and widest suspension bridges in the world. Its construction required overcoming numerous engineering challenges, particularly the need to withstand significant seismic activity and harsh weather conditions typical of the region. The bridge tower soars to heights of over 1,056 feet, making them among the tallest bridge towers globally. These towers support a massive deck that carries 8 lanes of traffic and 2 railway lines, facilitating both vehicular and rail transportation across the Bosphorus. The construction process of the Yavuz Sultan Selim Bridge involved the use of advanced engineering techniques and materials. Over 700,000 cubic meters of concrete and 150,000 tons of steel were used in the bridge's construction, ensuring its robustness and durability. One of the critical components of the bridge is its cable system, comprising over 1.4 million meters of steel wire, which was meticulously spun on site to create the main cables. These cables are designed to support the immense weight of the bridge deck while allowing for flexibility and movement, essential for withstanding the dynamic forces exerted by traffic, wind, and potential earthquakes. The bridge also features state-of-the-art aerodynamic elements to minimize wind resistance and ensure stability under various weather conditions. The construction team implemented a range of innovative safety measures, including advanced monitoring systems to continuously assess the bridge's structural health and detect any potential issues in real time. These systems are crucial for maintaining the bridge's integrity and ensuring the safety of the thousands of vehicles and passengers using it daily. The bridge's strategic importance extends beyond transportation, as it's also supporting economic activities by facilitating the efficient movement of goods and people across a major international transit route. Next up, it's time to travel over to Boston to talk about the Ted Williams Tunnel, which is a key component of the larger Central Artery project. The tunnel, which connects South Boston to Logan International Airport, was constructed to alleviate congestion and provide a direct route under Boston Harbor. Construction of the tunnel began in 1991 and was completed in 1995, with the tunnel officially opening to traffic in December 1995. The project is notable for being the first major tunnel in the United States constructed using an immersed tube technique. This method involved constructing the tunnel sections on land and then floating them to the site, sinking them into pre-dredged trenches on the harbor floor and connecting them underwater. The tunnel comprises 12 precast concrete sections, each approximately 325 feet long and weighing about 23,000 tons. These sections were built at a casting basin in East Boston, floated into position in Boston Harbor, and then carefully submerged into place. The construction of the tunnel required extensive dredging of Boston Harbor to create the trench where the tunnel sections would be placed. This dredging was a significant logistical challenge, given the need to manage harbor traffic and ensure the environmental safety of the surrounding waters. The trench was approximately 50 feet deep, with a width of around 90 feet. After the tunnel sections were placed in the trench, they were connected and sealed together to create a watertight structure. One of the most critical aspects of the tunnel's construction was ensuring the sections were perfectly aligned and securely connected underwater. To achieve this, engineers used a combination of hydraulic jacks, precise surveying equipment, and underwater divers. The alignment and sealing process required meticulous attention to detail to prevent leaks and ensure the long-term integrity of the tunnel. The tunnel structure is composed of high-strength concrete, reinforced with steel rebar to withstand the pressures of being submerged underwater and the loads from traffic above. The tunnel walls are 3 feet thick, providing significant durability and resistance to potential impacts or structural shifts. The interior of the tunnel features a ventilation system designed to manage vehicle emissions and ensure air quality within the tunnel, with large fans installed at intervals to circulate fresh air.
Another engineering challenge was the need to connect the submerged tunnel sections to the land-based approach structures on both sides of the harbor. This transition between the immersed tube and the cut-and-cover tunnels required careful design to accommodate the different construction methods and ensure a seamless connection. Let's investigate the Gran Gasoducto del Sur next. This is a major infrastructure project designed to transport natural gas from Venezuela to Argentina, passing through Brazil. This ambitious project aims to enhance regional energy integration and provide a reliable supply of natural gas to support economic growth and development in South America. Construction of the Gran Gasoducto del Sur began in 2015, with the project expected to span approximately 5,000 miles. The pipeline is designed to transport up to 50 million cubic meters of natural gas per day, providing a crucial energy source for industrial, commercial, and residential use. The pipeline will connect key natural gas fields in Venezuela with major consumption centers in Brazil and Argentina, enhancing energy security and reducing reliance on imported fuels. One of the significant engineering challenges of the Gran Gasoducto del Sur is the diverse terrain it traverses. The pipeline route includes dense forests, mountainous regions, and river crossings, requiring advanced engineering solutions and extensive environmental assessments. The project incorporates state-of-the-art technology for pipeline construction and monitoring, ensuring the safety and reliability of the gas supply. The total cost of the Gran Gasoducto del Sur is estimated at $23 billion. The project is expected to generate substantial economic benefits, including job creation, increased energy supply, and enhanced regional cooperation. Environmental and social considerations are integral to the Gran Gasoducto del Sur project. Comprehensive environmental impact assessments were conducted to minimize the impact on local ecosystems and communities. The project includes measures to protect biodiversity, manage water resources, and engage with local communities to address their concerns and ensure their participation in the project's benefits. But what about the Cross River Rail project in Australia? This $5.4 billion project involves the construction of a 10.2-kilometer rail line, including a 5.9-kilometer twin tunnel under the Brisbane River in the city center. Construction of the Cross River Rail began in 2019, with the project expected to be completed by the end of 2024. One of the primary challenges of this project is the need to construct the tunnels beneath a densely populated urban area. To minimize disruption to the city, tunnel boring machines are used to excavate the tunnels. These machines can efficiently and safely bore through the ground while minimizing surface disruptions. The project also includes the construction of 4 new underground stations, which are designed to accommodate high-capacity trains and provide modern, accessible facilities for passengers. The project also involves significant upgrades to existing infrastructure, including track realignment and station enhancements. These upgrades are designed to improve the overall capacity and efficiency of Brisbane's rail network, providing a more reliable and convenient service for passengers. Environmental and social considerations are a key focus of the Cross River Rail project. Measures are being implemented to minimize the environmental impact of the construction and operation of the rail line. By providing a reliable and efficient alternative to road transport, the rail line will help reduce traffic congestion and travel times for commuters. In addition to the construction jobs, the operation and maintenance of the rail line will create long-term employment opportunities, further contributing to economic growth and development. The Central Wan Chai Bypass in Hong Kong is a major infrastructure project designed to improve traffic flow and reduce congestion in the city. The project involves constructing a 4.5-kilometer long highway, including a 3.7-kilometer tunnel connecting Central and Wan Chai. The construction of the bypass involves advanced tunneling techniques, extensive earthworks, and the installation of modern traffic management systems. Tunneling for the bypass employs tunnel boring machines to excavate and install tunnel segments simultaneously. This method ensures the tunnels are structurally sound and minimize disruptions to the surface. The tunnels are lined with precast concrete segments, providing durable and waterproof structure. The construction of the highway involves extensive earthworks, including excavation, grading, and paving. The highway is designed to accommodate high traffic volumes, requiring precise engineering to ensure smooth and safe traffic flow. Additionally, the project includes the installation of modern traffic management systems, such as variable message signs and traffic cameras, to monitor and control traffic in real time. One of the significant challenges of the Central Wan Chai Bypass project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. Moreover, the bypass incorporates numerous sustainability features, such as noise barriers, green walls, and energy-efficient lighting. These elements reduce the environmental impact of the highway and enhance the quality of life for nearby residents. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency.
We have to travel over to France next for an impressive tunnel mega project. The Mont Cenis Base Tunnel, also known as the Mount Dambon Base Tunnel, is an ambitious and extensive infrastructure project currently under construction. Aimed at enhancing the high-speed rail connection between Lyon, France and Turin, Italy, this tunnel, set to become the longest rail tunnel in the world at 57.5 kilometers, represents a pinnacle of modern engineering and construction. The construction of the Mount Cenis Base Tunnel involves several advanced engineering techniques and significant logistical challenges. The project is managed by Tunnel Europen Lyon Turin and utilizes both conventional drilling and blasting methods, as well as state-of-the-art tunnel boring machines. The construction is divided into various sections, each with its unique geological challenges and engineering solutions. The tunnel's route from Saint-Jean-de-Maurienne in France to Susa in Italy passes through complex geological formations, including heavily fractured and sheared coal-bearing schists near the French portal. These geological conditions necessitate the use of traditional drilling and blasting methods in certain sections, particularly the initial 5 kilometers on the French side. TBMs are employed for the majority of the excavation, designed to handle both hard rock and softer ground conditions. The TBMs used are bi-mode machines capable of cutting through tough rock formations and using the Earth's pressure balance method in areas with sand or gravel. The project employs approximately 8,000 workers at its peak, who work on multiple fronts simultaneously. This massive workforce is engaged in the excavation of twin tunnels and numerous cross passages, which are essentially for safety and maintenance. In total, 164 kilometers of new tunnels are being excavated, including 4 access shafts and 204 cross passages. One of the significant engineering challenges is managing the logistics of such a large-scale project, especially with the limited access points available. For instance, the single access point provided by the Villeroden-Berget access adit constrains the movement of equipment and materials, requiring precise planning and coordination. The tunnel is designed to accommodate passenger trains traveling at speeds up to 135 miles per hour and freight trains at 75 miles per hour. This modal shift is expected to remove over 1 million lorries from the roads annually, resulting in substantial environmental and economic benefits. Construction progress has been substantial, with 13.5 kilometers of tunneling completed. The project employs 7 TBMs sourced from Schwenau, Germany, and they are equipped to work through both hard rock and soft substrates. The excavation process also involves extensive preparatory work, such as site clearance and the construction of new junctions to facilitate the movements of construction traffic without disrupting local communities. In addition to main running tunnels, the project includes the construction of numerous support structures. These include cross passages for safety and ventilation, access shafts, and underground emergency evacuation facilities. The project also features a sophisticated ventilation system to ensure safe and efficient air circulation throughout the tunnel. Let's move over to the next mega project. The Penang Second Bridge, officially named the Sultan Abdul Halim Muazzam Shah Bridge, is a remarkable feat of modern engineering in Malaysia. Opened to the public in 2014, this bridge stretches 15 miles across the Penang Strait, connecting Batu Kawan on the mainland to Batu Maung on Penang Island. As the longest bridge in Southeast Asia, it has significantly improved connectivity and economic activity in the region. The construction of the Penang Second Bridge was an ambitious project that took nearly 6 years to complete and cost $1.1 billion. The project involved thousands of workers and utilized advanced engineering techniques to overcome the challenges posed by the strait's deep waters and strong currents. The bridge's design features dual carriageways and 2 lanes in each direction, supported by a series of precast concrete segments. These segments were produced onshore and transported to the construction site, where they were carefully positioned using specialized equipment. This method ensured high precision and quality control, vital for the bridge's durability and safety. One of the most significant engineering challenges was constructing the main navigational span, which is 820 feet long and 100 feet high, allowing large vessels to pass beneath without obstruction. This span is supported by cable-stayed structures anchored to pylons rising from the seabed. The cables, made from high-strength steel, were meticulously tensioned to provide optimal support for the bridge deck, balancing the loads from traffic and environmental forces. To ensure the bridge's longevity, the construction incorporated several advanced features, including a robust foundation system. The piers were driven deep into the seabed to withstand seismic activity and the constant movement of the waters. Additionally, the bridge is equipped with a comprehensive monitoring system to track structural health and detect any potential issues in real time. It's time to move over to the state of Illinois now to talk about the St. Reges Chicago skyscraper project. Formerly known as Vista Tower, it's the 3rd largest building in Chicago, standing at 1,198 feet tall with 101 stories. The construction of this mixed-use skyscraper, which includes residential units, a hotel, and luxury amenities, presents numerous engineering challenges that required innovative solutions. The construction of the St. Regis Chicago began in 2016 and was completed in 2020. Designed by the renowned architect Jean Gang, the tower's distinctive design features 3 interconnected towers of varying heights, arranged in a staggering formation. This configuration not only creates a unique visual profile, but also plays a crucial role in the building's structural stability. One of the challenges was addressing the wind loads on the tall, slender structure. To mitigate these effects, the design includes a blow-through floor at the 83rd level. This open-air section allows wind to pass through the building, reducing wind-induced sway and improving overall stability. The use of this feature is a relatively new approach in skyscraper design and highlights the innovative engineering applied to the project. The building's core structure is composed of reinforced concrete, which provides the necessary strength to support the high-rise while allowing for flexibility under stress. The concrete core houses the building's elevators and utilities and is surrounded by steel frames that support the external cladding and the floor slabs. The use of high-strength concrete and advanced reinforcement techniques is essential in achieving the building's height and slender profile without compromising safety. The construction also involves significant logistical planning, particularly given the tower's location in the dense urban environment of Chicago's Lakeshore East neighborhood. The site's proximity to other high-rise buildings and active roadways required meticulous coordination to manage material deliveries, crane operations, and worker safety. The tower was constructed using a combination of traditional building techniques and modular construction, where certain components were prefabricated off-site and assembled on-site. This approach helped to accelerate the construction timeline and reduce the impact of the surrounding area. The St. Regis Chicago also features extensive underground construction, including a 6-level basement that houses parking facilities, mechanical rooms, and storage areas. Constructing these underground levels involved deep excavation and the installation of a complex foundation system designed to handle the significant loads of the skyscraper above. Next up, it's time to move over to the country of Uruguay, where the Punta del Tigre power plant stands. This natural gas-fired power plant is one of the largest in Uruguay, with a total generating capacity of 530 megawatts. Construction of the Punta del Tigre power plant began in 2013 and was completed in 2017. The project was implemented in 2 phases, with the first phase involving the construction of a 200-megawatt combined cycle unit and the second phase adding an additional 330-megawatt unit. The plant utilizes state-of-the-art technology to ensure high efficiency and low emissions, contributing to Uruguay's efforts to reduce its carbon footprint. One of the key features of the Punta del Tigre power plant is its flexibility. The plant can operate on both natural gas and diesel, providing a reliable source even in the event of disruptions to natural gas supply. This dual-phased capability enhances the plant's operational flexibility and energy security. The project faced several challenges, including the need to secure financing and manage environmental and social impacts. The total cost of the Punta del Tigre power plant was approximately $800 million. The
The project created numerous jobs during the construction phase and continues to provide employment opportunities in the operation and the maintenance of the plant. Environmental considerations were integral to the project. The plan incorporates advanced emission control technologies to minimize its environmental impact, and comprehensive environmental assessments were conducted to ensure compliance with local and international standards. The Punta del Tigre power plant plays a crucial role in Uruguay's energy landscape, providing a reliable and flexible energy source that supports the country's economic growth and development. We move over to Australia next for the Shell Prelude FLNG mega project. This $12.6 billion project involves constructing a massive floating platform, which is the largest floating structure ever built. The FLNG facility is 488 meters long, 74 meters wide, and weighs approximately 600,000 tons when fully loaded. The hull of the platform was constructed using high-strength steel to withstand the forces exerted by the waves, wind, and currents. The steel plates were fabricated in sections and then assembled onto large blocks, which were transported to the construction site and welded together. One of the key components of the FLNG facility is the topside, which houses the gas processing, liquefaction, and storage equipment. The topside modules were constructed using a modular approach, where each module was fabricated and pre-assembled off-site and then transported to the construction site for installation. The liquefaction process involves cooling the natural gas to minus 162 degrees Celsius, converting it into a liquid form for storage transport. The FLNG facility is equipped with advanced liquefaction technology, including cryogenic heat exchangers and refrigeration units. These systems are designed to operate efficiently and reliably in the challenging offshore environment. The construction of the facility also involved installing subsea infrastructure to connect the platform to the gas fields. This includes installation of subsea walls, flow lines, and risers, which transport the natural gas from the seabed to the platform. One of the key innovations in the project is using dynamic positioning technology to maintain the platform's position without requiring anchoring or mooring lines. The DP system uses thrusters and advanced control algorithms to counteract the forces of wind, waves, and currents, ensuring the platform remains stable and secure. The Rogfast Tunnel in Norway is a major infrastructure project designed to improve connectivity between the cities of Stavanger and Bergen. The tunnel, once completed, will be the longest and deepest undersea road tunnel in the world, spanning 27 kilometers and reaching depths of 390 meters below sea level. The construction of the Rogfast Tunnel involves advanced tunneling techniques, extensive earthworks, and the installation of modern traffic management systems. Tunneling for the Rogfast project employs tunnel boring machines to excavate and install tunnel segments simultaneously. This method ensures the tunnels are structurally sound and minimize disruptions to the surface. The tunnels are lined with precast concrete segments, providing a durable and waterproof structure. One of the significant challenges of the Rogfast Tunnel project is managing construction in a deep undersea environment. Engineers must carefully plan and execute construction activities to ensure the safety of workers and structural integrity of the tunnel. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. Moreover, the tunnel incorporates numerous sustainability features such as energy-efficient lighting, ventilation systems, and emergency response facilities. These elements ensure the safety and comfort of tunnel users and reduce the environmental impact of the project. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency. It's time to travel over to Turkey next for a record-breaking dam mega project. The USFI Dam stands at 275 meters tall, making it the highest dam located in Turkey and the fifth highest of its kind worldwide. Construction on the USFI Dam began in 2013 and culminated in 2022, transforming the landscape and significantly boosting Turkey's energy capacity. The dam is designed as a double curvature concrete arch structure. Its crest length extends 490 meters and the maximum crest elevation reaches 715 meters. This immense structure created a reservoir covering 33.63 square kilometers with a total storage capacity of around 2.2 billion cubic meters. Such a massive reservoir required the precise engineering and use of approximately 220 tons of steel for the gates and 3,800 tons of steel for the penstocks.
One of the critical components of the USFI Dam is its power generation capability. The dam houses a 558-megawatt hydroelectric power plant, equipped with 3 vertical axis Francis turbine units, each rated at 186 megawatts. These turbines are designed to operate with a head of 191 meters and discharge of 107 cubic meters per second. The power plant's annual electricity production capacity is approximately 1.9 billion kilowatt hours. The electricity generated is evacuated through a 380 kilovolt switchyard and transmission line, integrating it into Turkey's national grid. The construction of the USFI Dam faced numerous geological challenges due to the complex and fractured formations of the Choru Valley. Extensive geotechnical studies were conducted to understand the site conditions and plan the construction accordingly. Digital 3D geotechnical models were employed to manage the design and construction phases, providing a real-time data and enabling adjustments as excavation progressed. This innovative approach ensured the stability and safety of the dam structure. In addition to the dam and power plant, the project included the construction of significant ancillary infrastructure. 4 balanced cantilever viaducts were built, including the 644-meter-long Takeo Viaduct and the 695-meter-long USFI Viaduct. Moreover, the project involved constructing 110 kilometers of new roads, 45 tunnels, 22 bridges, and 92 culverts, all designed to support the dam's operation and enhance regional connectivity. The construction process required sophisticated equipment and techniques. The dam's height and curvature demanded precise engineering and the use of advanced construction machinery. Tower cranes with varying capacities, including one 12-ton 280 ECH tower crane, 2 10-ton 200 ECH tower cranes, and 4 6-ton 154 ECH tower cranes were utilized to handle the heavy lifting and placement of materials. Let's move over to the Rusy Bridge in Russia next. Spanning the eastern Bosphorus Strait, this bridge connects the Rusy Islands to the main city of Vladivostok. With a central span of 3,622 feet, the Rusy Bridge holds the record of the longest cable-stayed bridge span in the world. Its construction was a formidable challenge, given the harsh weather conditions and deep waters of the strait. The bridge's pylons rise to an impressive height of 1,053 feet, making them among the tallest bridge towers globally. The construction process was a massive undertaking, involving 5,000 workers at its peak. These workers faced extreme weather conditions, including strong winds and freezing temperatures, which required the use of specialized construction techniques and materials. The bridge's deck, supported by 168 cables, was designed to withstand the dynamic forces of both traffic and natural elements, ensuring stability and safety. Each cable, made from high-strength steel, was meticulously anchored and tensioned to maintain structural integrity of the bridge. One of the key engineering feats was the construction of the bridge pylons. These towering structures were built using advanced slip-form techniques, allowing for continuous and rapid construction despite the challenging weather. The pylons were anchored deep into the seabed using massive concrete foundations, providing the necessary support for the bridge's immense span. Additionally, the use of high-performance concrete and corrosion-resistant materials ensured the bridge's durability in the harsh marine environments. The Rusy Bridge also features state-of-the-art monitoring systems to continuously assess its structural health and detect any potential issues in real time. These systems are crucial for maintaining the bridge's integrity and ensuring the safety of thousands of vehicles and passengers that use it daily. Beyond its engineering achievements, the Rusy Bridge has significantly boosted the local economy by improving access to Rusy Island, which hosts major university and various research institutions. It's time to move over to Utah for the Salt Lake City International Airport redevelopment. Initiated in 2014, the project involves a complete overhaul of the existing facilities, including the construction of a new terminal and concourses, all aimed at modernizing the airport to handle increasing passenger demands and improving seismic resilience. The construction of the new terminal and concourses, involving several major contractors, is characterized by significant engineering challenges and innovative solutions. The first phase of the project, completed in 2020, included the construction of a 900,000 square foot terminal and the west portions of 2 linear concourses. This phase introduced 45 new gates and a 3,600 vehicle parking garage.
representing the largest public works project in Utah's history. A critical aspect of the construction was addressing the seismic risk, given the airport's proximity to the Wasatch Fault, an active seismic zone. To ensure the structural integrity of the new facilities, engineers installed 1,020 steel piles to support the foundations, ensuring the building could withstand potential earthquakes. These piles, driven deep into the ground, provide a stable base for the large terminal structures, which feature a 3-level design with expansive use of steel and concrete. The new terminal's design emphasizes both functionality and aesthetics, with the use of high-performance glazing and large open spaces that draw natural light into the building. This not only creates a welcoming environment for passengers, but also helps reduce energy consumption. The building's layout, with elevated roadways and separate levels of arriving and departing passengers, enhances traffic flow and minimizes congestion. Another significant feature of the project is the 7-mile-long baggage handling system, one of the most advanced in the country. This system, designed to efficiently manage the high volume of passenger baggage, includes large radius turns and wide conveyor belts, capable of handling oversized items like skis and golf clubs. The system is equipped with automated screening capabilities, reducing manual handling and enhancing the overall efficiency of airport operations. The construction of the new parking garage, which doubles the capacity of the previous facility, involved significant structural work. The garage was built using 90,000 cubic yards of concrete and 9,000 tons of rebar, ensuring its durability and capacity to accommodate the increased traffic expected with the airport's expansion. We have to travel over to Peru next, where the Peru LNG project is a major undertaking that is designed to export liquefied natural gas from the country to international markets. Located in Pampa, Melcarita, the project includes a gas liquefaction plant, a marine terminal, and a pipeline that transports natural gas from the Camasi gas fields in the Amazon basin to the coast. Construction of the Peru LNG project began in 2006 and was completed in 2010. The total cost of the Peru LNG project was approximately $4 billion. The liquefaction plant has a capacity of 4.4 million tons per year, making it one of the largest LNG facilities in South America. The project also includes a 408-mile pipeline, which traverses diverse terrains, including the Andes Mountains and coastal plains, to deliver natural gas to the liquefaction plant. Advanced engineering solutions were required to ensure the safe and efficient transport of natural gas, including the use of horizontal directional drilling to minimize surface disruption. The project also incorporated state-of-the-art technology for gas processing and liquefaction, ensuring high efficiency and low emissions. The total cost of the Peru LNG project was approximately $4 billion. Environmental and social considerations were conducted to identify and mitigate potential impacts on local ecosystems and communities. Let's travel over to Australia for the WestConnex project. This $16.8 billion development involves the construction of 33 kilometers of new and upgraded motorways, including tunnels, interchanges, and expressways. One of the significant engineering challenges in the WestConnex project is constructing the extensive tunnel network. The tunnels are built using tunnel boring machines, which can simultaneously excavate and line the tunnels with concrete segments. This method ensures a smooth and efficient construction process, minimizing disruption to the surface environment. The boring machines used in the project are some of the largest in the world, with diameters up to 15.5 meters. Another innovative aspect of the WestConnex project is using smart technology to manage traffic flow and improve safety. The motorways are equipped with an intelligent transport system that includes real-time traffic monitoring, electronic signage, and automated incident detection. This system helps manage congestion and ensures a swift response to any incident, enhancing the overall efficiency of the road network. Measures have been taken to minimize the environmental impact of the construction and operation of the motorways. This includes using low-emission construction equipment, implementing noise barriers, and green walls to reduce noise pollution. One of the key benefits of the WestConnex project is a significant reduction in travel times for commuters. By providing new and upgraded motorways, the project aims to alleviate congestion for some of Sydney's busiest roads, making it easier and faster for people to travel across the city. The Mersey Gateway Bridge in the United Kingdom is a major infrastructure project designed to improve the connectivity and reduce congestion in the Merseyside region. The bridge spans 1.2 kilometers across the River Mersey, providing a new crossing between Runcorn and Widnes. The construction of the bridge involves advanced engineering techniques, extensive earthworks, and the installation of modern traffic management systems. The bridge is a cable-stayed structure, featuring 3 pylons and a series of cables supporting the bridge deck. Constructing the pylons involves driving deep foundations into the riverbed, using reinforced concrete to ensure stability and durability. The cables are made from high-strength steel, capable of supporting the weight of the bridge deck and the traffic it carries. One of the significant challenges of the Mersey Gateway Bridge project is managing construction in a tidal river environment. Engineers must carefully plan and execute construction activities to minimize disruptions to river traffic and ensure the safety of workers and the environment. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. The bridge incorporates numerous sustainability features, such as energy-efficient lighting, stormwater management systems, and green spaces. These elements reduce the environmental impact of the bridge and enhance the quality of life for nearby residents. The construction also involves extensive public consultation and engagement to address concerns and ensure transparency.
But how about one of the biggest stadiums in the United Kingdom? The Tottenham Hotspur Stadium was completed in 2019 at a cost of approximately $1.5 billion. Transforming the historic White Hart Lane site in North London, the stadium incorporates cutting-edge design and innovative engineering solutions. The construction spanned 4 years and involved a peak workforce of over 3,800 people, working around the clock to meet the demanding schedule. A standout feature of the stadium is its structural steelwork. The east stand Y column supports level 3 of the stand, reducing the number of columns at ground level and allowing for a dramatic overhang of the facade. Above these columns, an additional transfer structure creates column-free spaces, enhancing the dynamic performance of the stand. The south stand tree structures support the massive 17,000-seat single-tier south stand. These structures consist of 8 individual branches meeting at a complex knuckle point, providing a robust support for the stand above the sliding pitch. The north stand features a cantilever that extends 10 meters over the tier below, using box section rakers supported by plan trusses. This design underwent extensive dynamic analysis to ensure the performance under load. The west stand is supported by 21-meter-tall slender steel box columns, creating a spectacular open space below with propped cantilever balconies and escalator platforms suspended from the structure above. One of the stadium's most innovative features is the world's first dividing retractable football pitch. This engineering marvel allows the grass surface to slide under the south stand to reveal an artificial turf beneath, enabling the stadium to host NFL games and other events. The retractable pitch is 105 meters long and 68 meters wide, and its movement is controlled with precision to maintain structural stability. The roof structure is another engineering highlight, featuring a lightweight cable net design with an outer compression ring and an inner tension ring. This design provides an unobstructed view for all spectators and enhances acoustics, creating an electric atmosphere during matches. The project faced several challenges, including integrating the new stadium into the dense urban fabric of North London and managing the complex logistics of such a large-scale construction site. The proximity to residential areas and the need to keep parts of the old White Hart Lane operational during the initial construction phases added to the complexity. Sustainability measures are a significant aspect of the stadium, including a commitment to zero waste to landfill and initiatives to reduce single-use plastics. The construction and operation of the stadium have significantly boosted the local economy, creating thousands of jobs and revitalizing the surrounding area. Next up, it's time to travel to Turkey. The Osman Gazi Bridge, completed in 2016, is a critical component of the country's infrastructure. The suspension bridge spans the Gulf of Izmit, connecting the town of Gebze and Yalova, and forms a vital part of the Istanbul and Izmir highway. With a total length of 1.7 miles and a main span of 5,472 feet, it is one of the longest suspension bridges in the world. Constructing the Osman Gazi Bridge posed numerous engineering challenges, primarily due to its location over the seismically active Gulf of Izmit. To address these challenges, engineers employed state-of-the-art seismic protection measures, including the installation of special bearings and dampers that allow the bridge to absorb and dissipate seismic activity. These features are crucial for ensuring the bridge's stability and safety in the event of an earthquake. The bridge's design includes two massive towers, each rising 837 feet above sea level, constructed using high-strength steel and concrete. These towers support the main cables, which are composed of over 130,000 miles of steel wire, meticulously spun on site to ensure optimal tension and load distribution. The main cables are anchored deep into the bedrock on either side of the gulf, providing a stable foundation for the entire structure. One of the key construction techniques used was the erection of the bridge deck in prefabricated sections. These sections weighed several hundred tons and were transported to the site by barges and lifted into place using specialized cranes. This method allowed for precise alignment and efficient assembly of the bridge deck, minimizing construction time and ensuring high-quality craftsmanship. The Osman Gazi Bridge significantly reduces travel time between Istanbul and Izmir, cutting the journey from 8 hours to just over 3 hours. The improvement has had a profound impact on the regional commerce and tourism, facilitating the efficient movement of goods and people. The bridge also enhances connectivity within Turkey's extensive transportation network, contributing to the country's economic development. But we have to move over to San Francisco next to talk about the extremely tall Salesforce Tower. Completed in 2018, this is a striking example of modern skyscraper engineering. Standing at 1,070 feet tall, it is the tallest building in San Francisco and one of the tallest in the western United States. The tower's construction required cutting-edge engineering to address both the aesthetic and functional demands of a high-rise building in a seismically active region. The foundation of the tower had to be exceptionally robust to ensure the building's stability during an earthquake. It's also supported by a massive concrete mat foundation that is 14 feet thick and sits atop over 42 steel-reinforced concrete piles driven deep into the bedrock. These piles reach depths of 300 feet below ground, anchoring the structure securely to withstand seismic forces. The building's core structure is composed of a high-strength steel frame designed to provide both flexibility and strength. It consists of movement-resisting frames, or MRFs, that allow the building to flex slightly during seismic events, dissipating the energy and reducing the risk of structural failure. The building also features a reinforced concrete core that houses the elevators and emergency stairwells, providing additional rigidity to the structure. The exterior of Salesforce Tower is clad in a curtain wall system made up of aluminum and glass panels. The system was designed to be both aesthetically pleasing and highly functional. The curtain wall includes high-performance glazing that reduces solar heat gain, thus lowering the building's cooling requirements. The facade's design also helps to minimize wind loads, which is critical for a building of this height. Construction of the tower involved the use of advanced construction techniques to manage the challenges of building in a dense urban environment. The tower was built using a top-down construction method, which allowed for the simultaneous construction of the superstructure and the below-grade levels, including the basement and foundation. This method not only sped up the construction process, but also minimized disruptions in the surrounding area. The crown of Salesforce Tower is another engineering feat. It includes a 150-foot sculptural extension that houses a unique LED art installation. This extension required a precise engineering to ensure it could withstand the wind and seismic forces while maintaining its aesthetic integrity. Let's travel over to Sal Paulo, one of the largest and most populous cities in Brazil. They are enhancing its public transportation infrastructure with the Sal Pao Metro Line number 6. Often referred to as the Orange Line, this project aims to alleviate the chronic traffic congestion in the metropolitan area. Spanning approximately 15 miles, Line 6 will connect the northwest region of São Paulo with the downtown area, providing a crucial link with daily commuters. Construction on the São Paulo Metro Line 6 commenced in 2015 but faced several delays due to the financial and administrative changes. However, the project gained momentum in recent years with a renewed commitment to completing this vital infrastructure. The line will include 15 stations, each designed to accommodate a significant number of passengers with modern facilities and accessibility features.
The stations are strategically located to serve densely populated neighborhoods, universities, and commercial areas, enhancing the overall connectivity of the city's metro network. One of the significant engineering feats of this project involves the use of tunnel boring machines to excavate the tunnels. These machines, known for their precision and efficiency, are capable of drilling through various soil types found in Sao Paulo. The machines also help minimize surface disruption, a critical factor in a bustling city. The tunnels are reinforced with precast concrete segments, ensuring their structural integrity and longevity. The expected daily ridership of the Sal Pao Metro Line 6 is projected to exceed 600,000 passengers, significantly reducing the number of vehicles in the road and thereby decreasing traffic congestion and pollution. The integration of this line with other metro lines and bus networks will provide seamless transit options for millions of residents and visitors. The project's budget is estimated at approximately $3 billion, reflecting its scale and complexity. The successful completion of Line 6 is anticipated to not only improve transportation efficiency, but also boost the local economy by creating jobs.
It's time to talk about the Jakarta-Bandung high-speed rail in Indonesia, which is an ambitious project aimed at significantly reducing travel time between Jakarta and Bandung from over 3 hours to approximately 40 minutes. With an estimated cost of $6 billion, this project is Indonesia's first high-speed rail venture. Construction began in 2016, focused on advanced construction techniques and technologies. One of the primary engineering challenges was the diverse terrain between Jakarta and Bandung, necessitating the construction of numerous bridges and tunnels. The line features 13 tunnels, including the Walini Tunnel, the longest at 4.5 kilometers. The construction of these tunnels employed tunnel boring machines, essential for efficiently and safely excavating through varied geological conditions. The rail line is designed to accommodate speeds up to 250 kilometers per hour, requiring the use of high-strength materials and precision engineering to ensure safety and stability. The tracks are laid on a slab track system, which provides greater durability and requires less maintenance compared to traditional ballast tracks. This system involves laying the rails on concrete slabs to fix in place with high-precision techniques to maintain the alignment and smoothness required for high-speed travel. A significant challenge faced during the construction was minimizing the impact on densely populated areas along the route. To address this, elevated tracks and viaducts were constructed in several sections, reducing the need for land acquisition and minimizing disruptions to local communities. Another critical aspect of the construction process was ensuring the rail line's resilience to seismic activity. Indonesia is located in a seismically active region, so the design incorporates earthquake-resistant features. These include flexible track systems and shock-absorbing materials that can withstand significant ground movement without compromising the rail line's integrity. Logistics played a crucial role in the project's success, given the scale and complexity of the construction. Materials and equipment had to be transported to various construction sites along the 142.3-kilometer route. This required a well-coordinated supply chain and efficient transportation network to ensure timely delivery and minimize delays. The Australia Pacific LNG project is one of the largest and most complex energy projects in the world. Located in Queensland, Australia, this project involves the extraction, processing, and transportation of natural gas from coal seams in the Surat and Bowen basins. The gas is then converted into liquefied natural gas for export to international markets. The project includes three main components: the gas fields, a 530-kilometer gas pipeline, and an LNG processing and export facility on Curtis Island. The construction of the gas fields involves drilling thousands of wells and installing extensive networks of gathering lines and processing facilities. These wells are drilled using advanced drilling techniques to reach deep coal seams and extract the gas. Hydraulic fracturing or fracking is employed to enhance gas flow, requiring precise control and monitoring to ensure environmental safety. The 530-kilometer gas pipeline is a critical component, transporting gas from the fields to the LNG facility. Constructing this pipeline involves trenching, welding, and laying pipes across diverse terrains, including forests, rivers, and farmland. Engineers use horizontal directional drilling to install the pipeline beneath major obstacles without disturbing the surface. This technique is particularly useful for crossing rivers and environmentally sensitive areas.
The LNG processing facility on Curtis Island is where the gas is cooled to -260 degrees Fahrenheit, transforming it into a liquid state for easier transport. This facility comprises liquefaction trains, storage tanks, and loading jetties. Each liquefaction train often involves complex engineering with compressors, heat exchangers, and cryogenic piping systems working together to cool and liquefy the gas. The storage tanks are massive, double-walled structures designed to safely store the LNG at extremely low temperatures. One of the significant challenges of the Australia-Pacific LNG project is the integration of its various components into a cohesive system. This requires meticulous planning, coordination, and execution to ensure all parts work seamlessly together. Additionally, the project must adhere to strict environmental and safety regulations, necessitating advanced monitoring and control systems to minimize environmental impact and ensure the safety of workers and surrounding communities. Moreover, the logistics of transporting such large volumes of natural gas require sophisticated shipping and handling facilities. The LNG is loaded into specially designed carriers equipped with advanced containment systems to prevent leakage and ensure safety during transit. These carriers transport the LNG to international markets where it's regasified and distributed through local gas networks.
Let's investigate the next mega project called the ATU Dam. Located on the Tigris River in southeastern Turkey, the project represents a major engineering and construction feat. This dam is a key component of Turkey's southeastern Anatolia project, which aims to harness the region's water resources for energy production, flood control, and irrigation. Construction of the ATU Dam began in 2006 and concluded in 2020. Standing 135 meters tall and stretching 1,820 meters across, the dam is a concrete-faced rock-filled structure. It has an embankment volume of 43.8 million cubic meters and creates a reservoir with a capacity of 10.4 billion cubic meters. This reservoir is essential for the dam's primary purpose of hydroelectric power generation, with an installed capacity of 1,200 megawatts from 6 Francis turbines, each producing 204 megawatts, generating about 3,833 gigawatt-hours of electricity annually. The dam's construction involves significant engineering challenges due to the region's complex geological and hydrological conditions. To manage these challenges, the Tigris River was diverted through 3 large circular diversion tunnels, each with a diameter of 12 meters and lengths ranging from 897 to 1,099 meters. This diversion was critical to keep the construction site dry, allowing for the building of the dam's foundation and ensuring a stable working environment. A key structural component of the ATU Dam is its sophisticated spillway system, designed to manage floodwaters efficiently. This system includes a chute and energy dissipation structures, crucial for controlling the flow of water released from the reservoir and protecting downstream areas from potential flooding. Additionally, the power plant, which houses the turbines, features state-of-the-art digital governors, shutoff valves, and ancillary systems to ensure efficient and reliable operation. Throughout its construction, the project encountered financial and logistical challenges. Initially funded by export credit agencies from Germany, Switzerland, and Austria, these backers withdrew in 2009 due to Turkey's inability to meet over 150 international environmental and social standards. Consequently, Turkey secured alternative funding through public and private bank loans, showcasing the government's commitment to completing the project despite international setbacks. The engineering work also included the construction of substantial infrastructure to support the dam. A 250-meter permanent steel girder bridge was built downstream to facilitate the transport of materials and equipment. Moreover, the project required extensive roadworks, including raising and repairing 52 kilometers of bridge to accommodate the construction needs. The powerhouse of the ATU Dam is equipped with 6 vertical Francis turbines, each with a capacity of 204 megawatts and 6 generators rated at 223 megavolt amperes. These components are housed in a facility designed to optimize efficiency and safety. The tail race tunnel, approximately 1,100 meters long with a maximum width of 143 meters, directs water safely away from the powerhouse, ensuring smooth operation. One of the significant engineering achievements of the ATU Dam is its ability to integrate advanced technology with practical construction methods. The dam's design and execution require a collaborative effort from various engineering and construction firms, employing modern techniques to address the region's unique challenges. We move over to Canada next, where the Confederation Bridge is located. Connecting Prince Edward Island to New Brunswick, the bridge is a marvel of modern engineering, completed in 1997. This 8-mile-long structure is the world's longest bridge over ice-covered waters, revolutionizing access to and from the island. The construction of this impressive bridge was an ambitious project that involved overcoming numerous engineering challenges posed by the harsh marine environment of the Northumberland Strait. The construction process employed over 5,000 workers and cost around 1 billion Canadian dollars. The design consists of a series of 44 high-performance concrete piers, each spaced approximately 820 feet apart. These piers were constructed on shore in a specially designed dry dock and then floated out to their positions using a fleet of barges. This method allowed for precise placement and alignment, ensuring the stability of the bridge. One of the most notable challenges was constructing the piers to withstand the extreme forces exerted by ice flows, which can reach thicknesses of up to 3 feet in winter. To address this, the piers feature an ice shield that deflects ice downward, breaking it into smaller, less forceful pieces. This innovative design ensures the bridge remains intact even during the harshest winter conditions. The superstructure of the Confederation Bridge, made from post-tensioned concrete, was designed for durability and minimal maintenance. Post-tensioning involves inserting high-strength steel cables through ducts in the concrete and then tensioning them to compress the concrete, significantly enhancing its strength and durability. This technique was crucial for ensuring the bridge could withstand the region's severe weather and temperature fluctuations. The bridge deck, rising to a height of 197 feet at its highest point, allows for passage of marine traffic. It carries 2 lanes of traffic and includes safety features such as a continuous concrete barrier and windshields to protect vehicles from the strong winds common in that area. The bridge is equipped with a sophisticated monitoring system that provides real-time data on structural health, ensuring its safety and longevity. Let's travel over to the state of Missouri to investigate Kansas City International Airport's transformed mega project. The airport has undergone a significant transformation with the construction of a new terminal, replacing the old 3-terminal layout that's been in use in the airport's opening since 1972. The new terminal spans approximately 1 million square feet and features a single consolidated structure that replaces the outdated horseshoe-shaped terminal. This design was intended to streamline operations and enhance passenger flow, reducing the complexity of navigating between different terminals. A key aspect of the construction was the airport's location on a former floodplain. Engineers had to ensure that the new terminal was built on solid ground that could withstand potential flooding. The site was prepared by excavating over 1.1 million cubic yards of soil and placing fill material to elevate the ground level, ensuring a stable foundation. In addition, extensive underground utilities were installed to support the terminal's operations. The new terminal structure is primarily composed of steel and reinforced concrete, providing both durability and flexibility. The use of structural steel allowed for large open spaces within the terminal, which is a significant improvement over the cramped and outdated spaces of the previous terminals. The roof of the terminal is supported by a series of large steel trusses, creating a vast column-free interior that enhances the feeling of openness and allows for better natural lighting. One of the challenging engineering aspects of the project was the integration of modern baggage handling and security systems. The terminal includes an advanced baggage handling system capable of processing thousands of bags per hour, which features such an automated sorting and tracking to improve efficiency and reduce the risk of lost luggage. The security checkpoints equipped with the latest screening technology, including automated screening lanes that expedite the process while maintaining high levels of security. The terminal's construction also included the development of new roadways and parking facilities to accommodate the increased passenger capacity. A new multi-level parking garage with over 6,000 spaces was built adjacent to the terminal, providing easy access for passengers and reducing the need for long shuttle rides from distant parking lots. The roads leading to the terminal were reconfigured to improve traffic flow and reduce congestion, with separate lanes for private vehicles, taxis, and buses. But we haven't talked about the Punta Catalina power plant yet. Located in the Dominican Republic, this coal-fired power plant has a total generating capacity of 752 megawatts, making it one of the largest power plants in the Caribbean. Construction of the Punta Catalina power plant began in 2013 and was completed in 2020.
The project involved the construction of 2 generating units, each with a capacity of 376 megawatts, as well as a supporting infrastructure such as a coal storage yard, a cooling water intake, and an ash disposal system. The plant utilizes advanced technology to ensure high efficiency and low emissions, contributing to the country's efforts to improve its energy security and environmental sustainability. One of the most important features of the Punta Catalina power plant is its environmental management system. The plant incorporates advanced emission control technologies, including flue gas desulfurization and selective catalytic reduction systems to minimize air pollutants. The project also includes measures to manage wastewater and solid waste, ensuring compliance with local and international environmental standards. The total budget of the Punta Catalina power plant project is approximately $2 billion, showcasing the country's great efforts. The project has generated significant economic benefits, including job creation during the construction phase and increased energy supply to support industrial commercial activities. Comprehensive environmental impact assessments were conducted to identify and mitigate potential impacts on local ecosystems and communities. The project also included measures to engage with local residents and address their concerns, ensuring that the benefits of the power plant are shared with the surrounding communities. Let's move over to the United States next, where the Silicon Valley Clean Water Project is located. This $500 million project involves constructing new treatment facilities and rehabilitating existing infrastructure to improve the efficiency and sustainability of the wastewater treatment process. The project includes the construction of a new wastewater treatment plant, which features advanced treatment technologies such as membrane bioreactors and ultraviolet disinfection. Membrane bioreactors are a combination of a biological treatment process and membrane filtration. They offer superior treatment performance compared to conventional methods, providing high-quality effluents by filtering out fine particles and microorganisms. Ultraviolet disinfection is another advanced technology employed by the project. UV disinfection involves exposing treated wastewater to ultraviolet light, which inactivates pathogens and microorganisms by damaging their DNA. This method is highly effective and does not involve the use of chemicals, making it an environmentally friendly alternative to traditional chlorination. This project also involves the rehabilitation of existing infrastructures, including replacing aging pipelines and upgrading pump stations. The pipelines are critical for transporting wastewater to and from the treatment plant. Engineers use trenchless technology such as cured-in-place pipelining to rehabilitate the pipelines without extensive excavation. This method involves inserting a resin-coated liner into the existing pipe and curing it in place, creating a new, durable pipe within the old one. Another critical component of the project is the construction of new storage and equalization tanks. These tanks are designed to manage the flow variations in the wastewater treatment process, ensuring a consistent and controlled flow of wastewater through the treatment plant. The construction of the Silicon Valley Clean Water Project also involves extensive earthworks to prepare the site for new facilities. This includes land grading excavation and soil stabilization. Land grading involves reshaping the land surface to achieve the desired elevations and slopes for the treatment plant. Sal Pao Metro Line 4 in Brazil is a critical infrastructure project designed to improve public transportation in the world's largest cities. The new metro line spans over 12 kilometers and includes 11 stations. The construction of Line 4 involves advanced tunneling techniques, station construction, and installation of modern train control systems. Tunneling for the new line employs tunnel boring machines to excavate and install tunnel segments simultaneously. This method ensures the tunnels are structurally sound and minimize disruptions to the surface. The tunnels are lined with precast concrete segments, providing a durable and waterproof structure. The construction of stations involves creating large underground spaces capable of accommodating thousands of passengers daily. Each station is designed with multiple levels, including concourses, platforms, and service areas. The construction process includes extensive excavation, concrete pouring, and steel reinforcement to create durable, safe, and accessible stations. The installation of modern train control systems is essential for the efficient operation of Line 4. These systems include automated train operation tech, which allows for driverless train operation, improving efficiency and reducing the risk of human error. The ATO system is integrated with an advanced signaling and communication system, ensuring smooth and safe train movements throughout the network. One of the significant challenges of the Sal Pao Metro Line 4 project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the project must adhere to strict environmental and safety regulations, requiring advanced monitoring and control systems to mitigate impacts. Furthermore, the project includes the development of comprehensive support infrastructure, such as maintenance depots and control centers, to ensure the long-term operation and maintenance of the metro system. These facilities are equipped with advanced diagnostic and maintenance tools to ensure the reliability and safety of the trains and infrastructure.
But have you ever seen a bridge that links two continents? The Bosphorus Bridge, officially known as the 15 July Martyrs Bridge, links Europe and Asia over the Bosphorus Strait in Istanbul, Turkey. Its construction, which took place from 1970 to 73, overcame significant engineering challenges due to the bridge's location and the environmental conditions of the strait. The idea of a permanent bridge across the Bosphorus dates back to antiquity, but it wasn't until the mid-20th century that this vision began to take shape. The design of the bridge was handled by British civil engineers Gilbert Roberts, William Brown, and Michael Parsons. Construction began in February 1970 with a team of 35 engineers and 400 workers. One of the primary engineering challenges was constructing the deep foundations required to support the bridge. These towers are anchored on massive caissons, which are watertight structures made of steel and concrete. The caissons were floated into position on the water and then gradually sunk by adding concrete, ensuring they reached the necessary depth to provide a stable foundation. This method was crucial to counteract the strong currents and seismic activity typical of the Bosphorus Strait. The bridge features a main span of 1,074 meters, making it one of the longest suspension bridges in the world at the time of its completion. The total length of the bridge, including the approach viaducts, is 1,560 meters. The deck, which accommodates 6 lanes of vehicular traffic, is suspended 64 meters above the water to allow for the passage of large maritime vessels. The deck's aerodynamic design minimizes wind resistance and reduces swaying, a critical consideration given the bridge's considerable length and height. The suspension system is composed of 2 main cables, each containing thousands of individual steel wires bound together. These cables are anchored in large concrete blocks on both ends of the strait, distributing the significant tension forces generated by the bridge's weight and the vehicles that cross it. Vertical suspender cables connect the main cables to the bridge deck, supporting and evenly distributing the load. The bridge towers, standing at 165 meters tall, were another significant engineering achievement. Constructing these towers involved precise engineering to ensure they could bear the load of the bridge and withstand environmental forces. The towers were built using steel sections that were fabricated off-site and then assembled on-site, a process that required meticulous planning and execution. Throughout the construction, engineers had to consider the unique environmental conditions of the Bosphorus Strait, including the strong currents and seismic activity. The bridge's design incorporates features to accommodate these conditions, such as flexible joints and specially designed bearings that allow the structure to move slightly, absorbing and dissipating energy from wind and earthquakes. The Bosphorus Bridge opened the traffic on October 30, 1973. Coinciding with the 50th anniversary of the founding of the Republic of Turkey. The completion of the bridge was a significant milestone in civil engineering, demonstrating the capabilities of suspension bridge design and construction techniques that continue to influence bridge projects worldwide. It's time to move to the Storebælt Bridge in Denmark, also known as the Great Belt Bridge. The bridge complex connects the islands of Zealand and Funen, significantly enhancing transportation and commerce in the region. The total length of the bridge system is approximately 11 miles, with the most impressive feature being the East Bridge, a suspension bridge with a main span of 5,328 feet, making it one of the longest suspension bridge spans in the world. Constructing the Storebælt Bridge was a complex task that involved overcoming numerous engineering and environmental challenges. The project required the efforts of 8,000 workers and cost approximately $3 billion. The East Bridge's 2 massive pylons, standing at 833 feet tall, were constructed using high-strength concrete and were anchored deep into the seabed to provide stability against the strong winds and currents of the Great Belt Strait.
One of the key engineering feats was the installation of the bridge's main cables, which are made up of 18,648 individual wires bundled together. These cables were meticulously spun on site and tensioned to support the enormous weight of the bridge deck, which carries both road and rail traffic. The deck itself is a marvel of modern engineering, designed to withstand the dynamic forces of wind, temperature changes, and the current weight of heavy traffic. The West Bridge, a box girder bridge, spans nearly 4 miles and carries both road and rail traffic. It required the construction of large concrete piers, which were precast on shore and then transported to their final positions using specially designed barges. This method ensured precision placement and minimized disruptions to the maritime traffic below. The Storbelt Bridge also includes a 5-mile-long tunnel, the world's second longest combined rail and road tunnel. This section was constructed using a combination of immersed tubes and bored tunnel techniques, ensuring a safe and efficient route for vehicles and trains. Next up, let's discuss the Glen Canyon Dam that's located on the Colorado River in Arizona. Constructed between 1956 and 1966, the dam was designed to provide water storage, flood control, and hydroelectric power generation for the southwestern United States. The dam created Lake Powell, one of the largest man-made reservoirs in the country, which extends into southern Utah. The construction of the Glen Canyon Dam was a massive undertaking that required extensive planning, innovation, and the overcoming of significant engineering challenges. The dam is a concrete arch-gravity structure standing 710 feet high and 1,560 feet long. It was designed to harness the power of the Colorado River while also providing a stable water supply for agricultural, industrial, and urban use in the region. One of the critical challenges during the construction of the Glen Canyon Dam was the remote location. The site, located in a remote area of the Colorado Plateau, was difficult to access, requiring the construction of roads, bridges, and other infrastructure to support the transport of materials and workers. The dam's construction also involved building the Glen Canyon Bridge, a steel arch bridge that spans 1,271 feet across the canyon, providing essential access to both sides of the construction site. To manage the Colorado River's flow during construction, engineers had to divert the river through tunnels carved into the canyon walls. 2 diversion tunnels, each with a diameter of 41 feet, were excavated through the sandstone bedrock on either side of the river. These tunnels, lined with concrete, allowed the river to bypass the construction site, ensuring that the dam could be built in a dry environment. The foundation of the dam required extensive preparation. Workers excavated the river beds down to solid bedrock and ensured a stable foundation for the massive concrete structure. The dam's foundation is key to its stability, allowing it to bear the immense pressure exerted by the reservoir. The concrete used in the dam was placed in blocks, each measuring about 50 feet square and 7.5 feet high. The dam was constructed in a series of these blocks, which were keyed and grounded together to form a solid monolithic structure. The dam's power plant, located at the base of the structure, houses 8 hydroelectric turbines that generate up to 1,320 megawatts of electricity. This power generation capacity has been vital in supporting the electric grid of the southwestern United States. The power plant is also equipped with a series of penstocks, large pipes that carry water from the reservoir to the turbines, allowing for the controlled water release and energy production. But have you ever heard about the construction of the Punta Pumarejo? This cable-stayed bridge spans the Magdalena River in Colombia, providing a critical transportation link between the eastern and western parts of the city and improving connectivity for the entire region. Construction of the Puente Pumarejo began in 2015 and was completed in 2019. The bridge is approximately 1.5 miles long and features a central span of 722 feet, supported by 2 main pylons rising 492 feet above the river. The bridge's design includes 4 lanes of vehicular traffic, as well as pedestrian and bicycle pathways, enhancing its accessibility and functionality. One of the significant engineering challenges of the Puente Pumarejo project was the need to accommodate the large volume of river traffic passing beneath the bridge. The bridge's clearance of 148 feet allows for the passage of large vessels, including cargo ships and riverboats, ensuring the continued flow of commerce along the Magdalena River. The construction process also involved advanced techniques for pile driving and cable installation, ensuring structural integrity and durability of the bridge. The bridge has generated significant economic benefits, including reduced travel times, increased trade, and enhanced regional connectivity. The project also has created numerous jobs during the construction phase and continues to support the local economic activities. We have to travel over to Singapore next, where the Jurong Island expansion project stands. This multi-billion-dollar project involves extensive land reclamation, construction of industrial facilities, and development of supporting infrastructure. The land reclamation process at Jurong Island uses advanced dredging equipment and techniques to ensure the stability and sustainability of the reclaimed land. Cutter suction dredgers and trailing suction hopper dredgers are used to excavate and transport sand from offshore borough areas to the reclamation site. The dredged material is then pumped into designated areas where it is compacted and stabilized to create a solid foundation for industrial facilities. The construction of industrial facilities at Jurong Island involves significant engineering and logistical challenges. These facilities include refineries, chemical plants, storage tanks, and pipelines, which require extensive planning and coordination to ensure safe and efficient operations. Utility infrastructure is another critical component of the Jurong Island expansion. This includes the installation of water supply and distribution systems, wastewater treatment facilities, and power generation and distribution networks. The water supply system involves constructing desalination plants and reservoirs to provide a reliable source of fresh water to industrial plants and substations to supply electricity to the industrial facilities. The power plants are designed to use natural gas as the primary fuel source, with backup generators to ensure a continuous power supply in case of outages. In addition to the construction of industrial facilities and infrastructure, the Jurong Island expansion also involves the development of supporting facilities such as offices, laboratories, and storage warehouses. These facilities provide the necessary support for the industrial activities and ensure the smooth and efficient operation of the petrochemical hub. The Qatar Metro is an ambitious urban rail project designed to transform public transportation in Qatar. This metro system comprises 4 lines: red, green, gold, and blue, spanning a total of 300 kilometers and including over 100 stations. The construction of Qatar Metro involves advanced tunneling techniques, station construction, and the installation of the state-of-the-art train control systems. Tunneling for the metro lines employs tunnel boring machines, which are large cylindrical machines that excavate and install tunnel segments simultaneously. These machines can operate 24/7, significantly speeding up the construction process. The tunnels are lined with precast concrete segments, which are assembled as the TBM advances. This method ensures the tunnels are structurally sound and resistant to groundwater ingress. Station construction involves creating large underground spaces capable of accommodating thousands of passengers daily. Each station is designed with multiple levels, including concourses, platforms, and service areas. The construction process includes extensive excavation, concrete pouring, and steel reinforcement to create durable, safe, and accessible stations. Additionally, the stations are equipped with advanced safety and ventilation systems to ensure passenger safety and comfort. The train control systems for the Qatar Metro are highly sophisticated, employing automated train operation technology. This system allows for driverless train operation, improving efficiency and reducing the risk of human error. The ATO system is integrated with advanced signaling and communication systems, ensuring smooth and safe train movements throughout the network. One of the significant challenges of the Qatar Metro project is managing construction in a densely populated urban environment. Engineers must carefully plan and execute construction activities to minimize disruptions to daily life and ensure the safety of workers and residents. Additionally, the extreme weather conditions in Qatar, particularly in the high temperatures, require special considerations for worker safety and construction materials. Furthermore, the project includes the development of a comprehensive support infrastructure, such as maintenance depots and control centers, to ensure the long-term operation and maintenance of the metro system. These facilities are equipped with advanced diagnostic and maintenance tools to ensure the reliability and safety of the trains and infrastructure.
Let's travel over to Sweden next, where the Varberg Tunnel is located. This project is part of Sweden's West Coast Line expansion, a significant infrastructure project designed to improve rail capacity and safety between Gothenburg and Lund. The tunnel project involves constructing a 3.1-kilometer tunnel beneath the coastal town of Varberg, featuring a combination of a 2.8-kilometer drill and blast rock tunnel and a 300-meter cut and cover tunnel. Construction of the Varberg Tunnel began in December 2019 with an estimated completion date of 2025. The project is being undertaken by the Swedish Transport Administration and involves a budget of approximately $620 million. The detailed design and construction work are being carried out by Implenia, a major player in the construction industry known for its expertise in large-scale tunneling projects. One of the most significant and challenging aspects of the Varberg Tunnel is dealing with the unique geological conditions. The rock in the northern part of the tunnel, primarily chalkenkite, poses significant difficulties for drilling. To address these challenges, the construction team employs advanced techniques such as rock bolting for structural support and pressure grouting to manage water ingress. The main tunnel's cross-section measures 75 square meters, while the service tunnel has a cross-section of about 20 meters, with various cross passages connecting the two. The Varberg Tunnel is part of a broader plan to enhance the West Coast Line, which is a vital transit route connecting southern Sweden to Copenhagen and other parts of Europe. The project aims to facilitate the accommodation of more trains, thereby improving overall rail efficiency and reliability. It includes the removal of the existing railway track and the relocation of the freight yard to the north of Varberg, which will help remove the barrier effect in the central area of the city and improve connectivity with the sea. The new Varberg station, located 150 meters north of the current one, is also part of the project. This station will feature submerged platforms and modern amenities such as cafes, shops, and restaurants. The station's design includes a granite stone base with a wave pattern and an upper section made of wood with a wave-shaped ceiling, blending functionality with aesthetic appeal. In addition to the tunnel and the new station, the project involves constructing several bridges, a 1.3-kilometer cutting and approximately 2.7 kilometers of new track. Notably, the Gasoducto Bridge, a key component of the project, is being built to allow the double-deck track to pass beneath it. Maintaining railway operations during construction is crucial, necessitating meticulous planning and coordination to minimize disruptions. The existing railway line continues to function throughout the construction phase, ensuring the rail services remain uninterrupted. Next, we turn our attention to the Humber Bridge in the United Kingdom, an iconic landmark in the realm of bridge construction. Completed in 1981, the Humber Bridge held the record as the world's longest single-span suspension bridge until 1998, with a main span measuring an impressive 4,626 feet. This feat of engineering connects the East Riding of Yorkshire with North Lincolnshire, significantly improving travel times and boosting economic ties between the two regions. Constructed at a cost of approximately £98 million, which would equate to around $500 million today, the Humber Bridge was a monumental project of its time. The design and construction of the Humber Bridge posed numerous challenges, not least of which was its location over the Humber estuary, known for its deep waters and strong tidal currents. The bridge's two massive towers, each rising 510 feet above the water, were constructed using a combination of reinforced concrete and steel, providing the necessary strength and stability to support the immense weight of the bridge deck. The main cables, each composed of 14,948 strands of high-tensile steel wire, were spun in situ using a complex and labor-intensive process that ensured they could withstand the forces exerted by the span and the variable weather conditions. One of the key construction techniques involved the use of floating caissons for the foundations, which were sunk into the estuary bed to provide a stable base for the towers. This method required precise engineering and careful coordination to ensure the caissons were placed accurately and securely. Additionally, the bridge was designed to allow for thermal expansion and contraction, as well as the dynamic loads imposed by traffic and wind, incorporating expansion joints and flexible cables that could accommodate these movements. But we have to talk about the largest LNG projects ever in the United States. The Rio Grande LNG terminal, located at the port of Brownsville in Texas, aims to become a major LNG export facility that will handle up to 27 million tons per annum of liquefied natural gas once fully operational.
The terminal's design includes significant infrastructure, such as multiple LNG storage tanks, each capable of holding 180,000 cubic meters of LNG, and 2 marine berths to accommodate LNG carriers of up to 185,000 cubic meters capacity. One of the engineering challenges of the project is the site's location along the Brownsville Ship Channel, a highly active industrial waterway with specific environmental and logistical requirements. The construction site required extensive preparation, including soil stabilization and the installation of a comprehensive levee system around the perimeter to protect against flooding and manage stormwater runoff. The soil stabilization process involved deep mixing techniques to ensure a solid foundation for the massive structures, particularly in the areas where the liquefaction trains and storage tanks are being built. The LNG production process at the terminal involves cooling natural gas to -162 degrees Celsius to liquefy it, reducing its volume by about 600 times for easier storage and transportation. This process demands substantial energy, requiring the installation of robust power generation facilities and cooling systems. The engineering work includes laying down extensive pipelines to bring feed gas to the site and distributing it to the liquefaction trains. The liquefaction trains themselves are highly complex systems, each containing multiple stages of compression and heat exchange to achieve the necessary cooling of the gas. These trains are built using modular construction techniques, allowing large components to be prefabricated off-site and then transported to Brownsville for assembly. This approach minimizes on-site construction time and reduces potential delays. The terminal also includes significant safety and monitoring systems. Given the flammable nature of LNG, the design integrates advanced fire detection and suppression systems, extensive monitoring of gas leaks, and robust emergency response plans. Additionally, the terminal will feature a network of control rooms and automation systems to manage the operation of the liquefaction trains, storage tanks, and loading berths efficiently and safely. The engineering behind the Rio Grande LNG terminal also includes provisions for future expansion. The site's being prepared to potentially add additional liquefaction trains and storage capacity as market demands grow. This forward-thinking approach to the terminal's design ensures that it can adapt to future energy needs. But what about a brand new tunnel that's currently being built? The Tunnel del Toyo, currently under construction in Colombia, is set to become the longest road tunnel in Latin America, spanning approximately 6.2 miles. This ambitious project aims to significantly reduce travel time between Medellin, Colombia's second-largest city, and the key port of Urabá. This reduction in travel time is expected to boost trade and economic activities in the region. Construction of the Tunnel del Toyo began in 2015, and the project is expected to be completed by late 2024. The tunnel will cut through the rugged Andean mountains, presenting numerous engineering challenges. The project involves extensive geological surveys and the use of advanced tunneling techniques to navigate the complex terrain safely. The Tunnel del Toyo is designed as a dual-bore tunnel, with each bore accommodating 2 lanes of traffic. This design ensures a smooth flow of vehicles and enhances safety. The project also includes the construction of access roads and ventilation systems to maintain air quality within the tunnel. One of the critical benefits of the Tunnel del Toyo is the expected reduction in travel time. Currently, the journey between Medellin and Urabá takes about 6 hours by road, traversing winding mountainous roads that are often prone to landslides and other hazards. The tunnel will cut this travel time to approximately 3 hours, providing a more direct and safer route. The Tunnel del Toyo project is estimated to cost around $1 billion, with funding sourced from both national and regional governments. Environmental considerations are also a key aspect of the project. The construction process includes measures to minimize the impact on local ecosystems, such as the relocation of wildlife and reforestation efforts. The tunnel's design also incorporates advanced drainage systems to manage water flow and prevent flooding. Let's investigate the Bogotá Metro project next, which is located in Colombia. The first line of this metro development, costing approximately $4.3 billion, will stretch over 24 kilometers and include 16 stations, serving millions of residents in Bogotá. Construction of the Bogotá Metro began in 2020, with the project expected to be completed by 2028. One of the primary challenges of this project is the dense urban environment in which it began to be constructed. To minimize disruptions to the city, much of the metro line is being built underground, requiring extensive tunneling and excavation work. The use of tunnel boring machines is essential for this task, as they can efficiently and safely excavate the tunnels while minimizing surface disruptions. The Metro Line is designed to accommodate high-capacity trains that can transport up to 72,000 passengers per hour. One of the innovative aspects of the Metro project is the integration of advanced signaling and control systems. The Metro will use a communication-based train control system, which allows for real-time monitoring and control of train movements. The construction of the Metro also involves significant coordination with existing infrastructure and utilities. Engineers must carefully plan and execute the tunneling and excavation work to avoid disrupting critical services such as water, electricity, and telecommunications. This requires detailed mapping and analysis of the underground environment, as well as the use of advanced construction techniques to ensure the stability and integrity of the surrounding infrastructure. The Bogotá Metro is expected to have a transformative impact on the city's transportation system. By providing a reliable and efficient alternative to road transport, the Metro will help reduce traffic congestion and travel times for commuters. The Great Man-Made River Project in Libya is one of the largest and most ambitious water supply projects in the world. The project aims to transport water from underground aquifers in the southern desert to the coastal cities in the north. The construction involves digging massive tunnels, laying pipelines, and building pumping stations. The project includes over 1,750 miles of pipeline, making it one of the longest water supply networks in the world. Constructing these pipelines involves extensive excavation, welding, and laying of large-diameter pipes. The pipes are made from pre-stressed concrete, reinforced with steel to ensure durability and longevity. One of the significant challenges of the Great Man-Made River Project is managing the environmental impact and ensuring the sustainability of the water supply. Engineers must carefully monitor the aquifers to prevent over-extraction and depletion of the water resources. Additionally, the construction process must adhere to strict environmental regulations to minimize disruptions to the desert ecosystem. Moreover, the project's scale and complexity require advanced construction techniques and materials. The tunnels are constructed using tunnel boring machines, which excavate and reinforce the tunnel walls simultaneously. This method ensures the tunnels are structurally sound and minimizes disruptions to the surface. The pumping stations are equipped with advanced pumps and control systems to manage the water flow and pressure throughout the network.
It's time to talk about a brand new megatall skyscraper that was recently built in Poland. Warsaw Tower is located in Warsaw, Poland, and stands at 310 meters tall, making it the tallest building in the European Union. The project, developed by HB Reavis and designed by Foster Plus Partners, began construction in 2015 and concluded in 2022. The towering structure is a key component of the Warsaw Place mixed-use development, which includes Warsaw 1 and Warsaw 2 with heights of 81 and 90 meters. The construction of Warsaw Tower presented numerous engineering challenges, particularly due to its proximity to Warsaw's Central Railway Station. To address the high water table and poor soil conditions, engineers implemented a deep foundation system with piles extending up to 36 meters below ground. These piles are essential for supporting the tower's immense weight and ensuring long-term stability. The tower's superstructure consists of a reinforced concrete core and steel framework. The concrete core, housing the elevators and emergency staircases, provides the primary vertical support. Surrounding this core is a steel framework made up of high-strength steel beams and columns. This hybrid construction approach allows for large open floor plans with minimal internal columns, maximizing the usable office space and providing flexibility in office layouts. The facade of Warsaw Tower incorporates advanced engineering techniques to enhance energy efficiency. The triple-glazed curtain walls provide excellent thermal insulation and reduce energy consumption. Automated sharing devices integrated into the facade adjust according to the sun's position, optimizing the building's energy performance. The spire of Warsaw Tower, which adds 80 meters to its height, is a remarkable engineering achievement. Constructed in sections, each weighing up to 250 tons, the spire was assembled using advanced cranes and the expertise of professional climbers. The spire serves as both aesthetic and functional purposes, housing maintenance platforms and supporting antennas. Inside Warsaw Tower is designed for modern office needs, with 70,000 square meters of premium office space. The office floors feature a clear height of 3 meters, allowing for spacious open-plan layouts that can be easily reconfigured. High-capacity double-deck elevators serve the offices, with each car serving 2 floors simultaneously to reduce waiting times and improve efficiency. The tower also includes a public observation deck on level 53, offering panoramic views of Warsaw, and a rooftop terrace with greenery on level 49, creating the highest garden in the city. The construction process also is emphasizing sustainability and future-proofing. Early in the project, a thorough analysis of potential innovation solutions was conducted, leading to the strategy that positively impacts the building's performance. The sustainability strategy includes measures to reduce water and energy consumption, contributing to the building's certification. Let's move over to the United States for the New River Gorge Bridge. Spanning 3,030 feet across the New River Gorge, this arch bridge boasts a main span of 1,700 feet, making it one of the longest single-span arch bridges in the world. The bridge sits 876 feet above the New River, offering breathtaking views and dramatically improving transportation in the region. The construction of the New River Gorge Bridge was a monumental task, requiring innovative solutions to the challenges posed by the gorge's rugged terrain and the river below. The design utilizes a steel arch chosen for its strength and ability to span long distances without the need for support piers in the river, which would have been difficult to construct and maintain. One of the most impressive aspects of the construction process was the method used to assemble the arch. Prefabricated sections were lifted into place using cables strung across the gorge. This method required precise engineering and coordination to ensure each section was correctly aligned and secured. The steel used in the bridge's construction was specially treated to withstand the area's environmental conditions, ensuring its durability and longevity. The bridge's deck, supported by the arch below, carries 4 lanes of traffic and has significantly reduced travel times between the region's communities. Before the bridge's construction, travelers had to navigate a treacherous 40-minute journey down narrow, winding roads to cross the gorge. The New River Gorge Bridge has cut the travel time to less than a minute, fostering development and improving access to the area's natural beauty. Let's navigate the stunning Frederick Douglass Memorial Bridge. Located in Washington, D.C., this iconic infrastructure project is designed to replace the aging South Capitol Street Bridge, which had become functionally obsolete. Construction of the new bridge began in 2018 and was completed in 2021. This project represents one of the largest infrastructure investments in the history of the District of Columbia, with the bridge spanning 1,600 feet across the Anacostia River and featuring 3 prominent arch structures that define its aesthetic and structural integrity. The bridge's design includes 6 traffic lanes, as well as dedicated paths for bicycles and pedestrians, providing enhanced multimodal transportation options. The structure is supported by massive piers sunk deep into the riverbed, ensuring stability and resilience against the forces of the river and the dynamic urban environment. One of the key engineering challenges of the Frederick Douglass Memorial Bridge was constructing its large, sweeping arches. These arches are made from high-strength steel and were assembled on-site using precise construction techniques to ensure their alignment and structural performance. Each arch was constructed in segments, lifted into place by cranes and carefully connected. The assembly required detailed planning and execution to manage the complex geometry and the loads transferred through the arches into the foundation piers. Another critical aspect of the bridge's construction involved the use of modern materials and methods to extend the lifespan of the structure and minimize maintenance needs. The bridge deck is supported by a system of cables anchored at the top of arches and connected to the deck, which helps to evenly distribute the load across the structure. These stay cables are tensioned to provide the necessary support, while allowing for flexibility and movement under traffic loads and thermal expansion. The foundation work was particularly challenging due to the bridge's location over the Anacostia River. The construction team employed cofferdams, temporary water weight enclosures pumped dry to create a dry work environment below the waterline. These cofferdams allowed workers to excavate and install deep foundations that anchor the bridge piers securely into the riverbed. Additionally, the construction process had to consider the tidal nature of the river and the varying water levels. The bridge also incorporates advanced drainage and stormwater management systems to handle runoff from the roadway. These systems are designed to reduce the environmental impact on the Anacostia River by capturing and treating stormwater before it enters the waterway. It's time to talk about the Aku Superport located in São João da Barra, Brazil.
This deep-water port is designed to handle a wide range of cargo, including oil, iron ore, and containerized goods, providing a critical gateway for Brazil's exports and imports. Construction of the Aku Superport began in 2007, and the project was completed in phases with full operational capacity achieved in 2015. The port complex covers an area of approximately 130 square miles and features multiple terminals, including a dedicated oil terminal, an iron terminal, and a container terminal. The port's deep-water berths can accommodate some of the largest vessels in the world, including very large crude carriers and Cape-size bulk carriers. One of the significant engineering challenges of the Aku Superport project was the construction of the port's extensive infrastructure. This included the dredging of deep-water channels, the construction of breakwaters, and the development of onshore facilities such as storage tanks and conveyor systems. The project also involved the installation of advanced navigation and safety systems to ensure the safe and efficient movement of vessels. The price tag of this immense undertaking is $2.5 billion. The port has generated significant economic benefits, including increased trade, job creation, and the development of associated industries such as logistics and manufacturing. We have to talk about the port of Dam next, which is located in Oman. This $10 billion project covers an area of 2,000 hectares and includes the construction of port facilities, industrial zones, and residential areas. Construction of the Port of Duke began in 2011, with the project expected to be completed by 2025. One of the primary challenges of this project is the remote location, which requires extensive infrastructure development to support the construction and operation of the port. This includes the construction of roads, utilities, and housing for workers, as well as the development of logistics and supply chain networks. The port facilities are designed to accommodate a wide range of vessels, including container ships, oil tankers, and bulk carriers. The construction of the port involves significant dredging and reclamation work to create deep-water berths and turning basins. This requires the use of advanced dredging equipment and techniques to ensure the stability and safety of the port structures. Dredging operations at the Port of Duke utilize cutter suction dredgers and trailing suction hopper dredgers to excavate and transport sediment from the seabed. These dredgers are capable of handling various soil conditions, from soft silt to compacted sand and rock. The construction of the port quay walls and breakwaters involves significant engineering challenges. The quay walls are constructed using precast concrete blocks and steel sheet piles driven deep into the seabed. These structures provide the necessary strength and durability to withstand the forces exerted by large vessels and the harsh marine environment. The quay walls are built using a combination of precast concrete blocks and in-situ concrete casting. The precast blocks are manufactured off-site to ensure quality and consistency, then transported and installed using heavy-duty cranes. The sheet piles are driven into the seabed using hydraulic pile drivers, which provide the necessary force to penetrate the dense seabed material. Giga Berlin is Tesla's first European gigafactory, located in Brandenburg, Germany. This massive facility is designed to produce electric vehicles and batteries, significantly expanding Tesla's production capacity. The construction of Giga Berlin involves extensive site preparation, building construction, and the installation of advanced manufacturing equipment. Site preparation includes clearing and leveling the land, as well as installing utility infrastructure such as water, electricity, and sewage systems. This process requires careful planning and execution to ensure the site is ready for construction. The main buildings of Giga Berlin are constructed using prefabricated steel frames and panels, allowing for rapid assembly and scalability. These buildings include production lines, assembly areas, and administrative offices. The construction process involves extensive coordination between various contractors and suppliers to ensure all components are delivered and installed on time. One of the significant challenges of Giga Berlin is the installation of advanced manufacturing equipment. This equipment includes robotic assembly lines, battery production machines, and quality control systems. Installing and calibrating this equipment requires precision engineering and technical expertise to ensure optimal performance. Additionally, Giga Berlin incorporates numerous sustainability features, such as solar panels, rainwater harvesting systems, and energy-efficient HVAC systems. These elements reduce the facility's environmental impact and align with Tesla's commitment to sustainability. The construction also involves extensive collaboration with local authorities and communities to address concerns and ensure compliance with regulations. Next up, we travel over to the country of Nigeria to talk about the Third Mainland Bridge. Originally opened in 1990, the Third Mainland Bridge spans 11.8 kilometers and is the longest of 3 bridges connecting Lagos Island to the mainland. The expansion and rehabilitation project, costing approximately $300 million, focuses on addressing structural wear and improving traffic flow in one of Africa's most populous cities. Construction commenced in 2018 with a focus on repairing the bridge's deteriorating sections and enhancing its structural integrity. One of the primary engineering challenges was the need to work on a live bridge that supports over 100,000 vehicles daily. To minimize disruptions, the project was executed in phases with specific sections of the bridge closed for repair while traffic was rerouted to alternate routes. This required precise planning and coordination to ensure safety and efficiency. The rehabilitation work involved several advanced engineering techniques. Structural assessments revealed issues with the bridge's expansion joints, bearings, and docking. To address these, engineers employed high-pressure water jets to remove deteriorated concrete and replaced it with high-performance materials that offer greater durability. The expansion joints, critical for accommodating thermal expansion and contraction, were replaced with modern flexible joints designed to withstand heavy traffic loads and environmental conditions. In addition to structural repairs, the project included the installation of new asphalt overlays to improve the road's surface. This involved milling the existing surface to create a suitable base for the new asphalt layers. Engineers use state-of-the-art paving machines to ensure smooth and even surfaces, essential for enhancing driving comfort and reducing wear and tear on vehicles. One of the innovative solutions employed in the project was the use of underwater drones to inspect and repair the bridge's underwater supports. These drones, equipped with high-definition cameras and sonar technology, provided detailed images and data on the condition of the submerged structures. The successful completion of the Third Mainland Bridge expansion is expected to significantly improve traffic flow and safety in Lagos, reducing congestion and travel times for commuters. But we have to talk about the iconic skyscraper next, located in Sweden. The Turning Torso, located in Malmö, is a residential skyscraper known for its unique twisting design. Designed by Santiago Calatrava, this structure stands 190 meters tall and was completed in 2005. Its construction involved advanced engineering techniques to achieve its distinctive form and ensure stability and functionality. The Turning Torso is composed of 9 stacked pentagonal segments that rotates 90 degrees from the base to the top. Each segment consists of 5 floors, with a total of 54 stories. The building's core is a reinforced concrete cylinder which acts as the main structural support, housing the elevator shafts and staircases. The core is completed by an external steel exoskeleton that provides additional support and wind resistance. The foundation of the Turning Torso is particularly noteworthy. The foundation is a cylindrical box 30 meters in diameter and 15 meters deep, resting on solid limestone bedrock 15 meters below the ground. This ensures the building's stability and minimizes the risk of differential settlement. Piles driven into the bedrock provide further support, preventing unacceptable bending or swaying. The construction progress began with the core, which was built using a sliding formwork system. This method involves a form that climbs upwards as each floor is completed, allowing continuous construction without needing to dismantle and reassemble the framework for each level. The walls around the staircase and lifts were poured into forms suspended from the sliding form, ensuring precision and alignment. Once the core was established, the external steel framework was assembled. This exoskeleton is composed of tapered white steel tubes that wrap around the building, connecting to the core at each level. These tubes are also crucial for the building's lateral stability, helping to resist wind forces and reduce vibrations. The steel framework also supports the triangular sections of each floor, which extend out from the core. Each floor is constructed of prefabricated concrete slabs that fit together like pieces of a puzzle, rotating slightly to create an overall twist. These slabs are anchored into the core and the external steel framework, ensuring a cohesive and stable structure. The slabs are prefabricated off-site to ensure precise specifications, reducing construction time and improving quality control. The facade of the Turning Torso is clad in a curved aluminum panels designed to follow the building's twists. The windows are arranged to lean either inward or outward, maintaining the flow lines of the design and providing residents with unique views. The facade not only contributes to the building's aesthetic appeal, but also enhances its thermal performance and durability. One of the significant challenges during the construction was managing the twisting geometry while maintaining structural integrity.
Engineers used advanced computer modeling and simulation techniques to predict and manage the stresses and loads of the building. These models helped ensure that each segment aligned properly and correctly, and that the building's overall stability was maintained throughout the construction process. Let's talk about the Erasmus Bridge in Rotterdam, Netherlands, stretching 2,631 feet across the Numas River. This cable-stayed bridge is notable for its single asymmetrical pylon that rises 456 feet into the air. The bridge connects the northern and southern parts of Rotterdam, enhancing the city's infrastructure and promoting economic growth. The construction of the Erasmus Bridge prevented numerous engineering challenges, particularly due to its unique design and the heavy traffic it needed to support. The bridge's pylon, made of 8,000 tons of steel, was constructed on site using advanced techniques to ensure its stability and strength. The pylon's asymmetrical design required precise calculations and innovative construction methods to balance the forces exerted by the bridge's cables and deck. One of the key features of the Erasmus Bridge is its cable-stayed design, which includes 40 steel cables that fan out from the pylon to support the bridge deck. These cables were carefully tensioned to ensure even distribution of weight to minimize the movement under dynamic loads such as wind and traffic. The bridge deck itself is constructed from steel and concrete, providing the necessary strength to support both vehicular and pedestrian traffic. During construction, engineers faced the challenge of building the bridge over a busy waterway without disrupting river traffic. To address this, the main span of the bridge was built off-site and floated into position using barges. This method allowed for precise placement and minimized interruptions to the bustling port activities below. The Erasmus Bridge also incorporates a 300-foot bascule bridge section, which can be raised to allow larger ships to pass through. This section is one of the largest and heaviest bascule bridges in the world, with a counterweight system that ensures smooth and efficient operation. Since its completion, the Erasmus Bridge has become a vital artery for Rotterdam, significantly improving traffic flow and accessibility. Next up, we have to talk about the Arena da Amazônia. Located in Manaus, Brazil, this iconic structure not only serves as a venue for major sporting events, but also as a cultural and community hub for the region. Construction of the Arena da Amazônia began in 2010 and was completed in 2014, just in time for the World Cup. The stadium has a seating capacity of approximately 44,000 and features a distinctive design inspired by the Amazon rainforest. The roof structure resembled a basket weave, reflecting the local cultural heritage and providing the aesthetically striking appearance. One of the significant engineering challenges of the Arena da Amazônia was its location. Manaus is situated in the heart of the Amazon rainforest, presenting logistical challenges for transporting construction materials and equipment. The project required meticulous planning and coordination to ensure timely completion while minimizing the environmental impact. The stadium incorporates several sustainable design features, including rainwater harvesting systems, natural ventilation, and energy-efficient lighting. These features not only reduce the environmental footprint of the stadium, but also enhance the comfort and experience of spectators. The use of local materials and labor also has hosted numerous international and domestic football matches, as well as concerts and cultural events. It has become a symbol of pride for the people of Manaus and a key attraction for tourists visiting the region. The stadium's design and construction have also received accolades for their innovation and sustainability. But we haven't talked about the Maputo-Katembe Bridge yet, located in Mozambique. Construction of this bridge began in 2014 and was completed in 2018. One of the primary engineering challenges was constructing a bridge that can span the wide expanse of Maputo Bay while withstanding the region's environmental conditions. The bridge features a main span of 680 meters, supported by two massive towers that rise 137 meters above the water. The construction of the bridge's towers involved using high-strength concrete and reinforced steel. The towers were constructed using slip-form construction techniques, where concrete is continuously poured into a moving formwork that gradually climbs the structure. This method allows for more efficient and continuous construction of tall structures with consistent quality. The towers were designed to withstand strong winds and seismic activity, ensuring the bridge's stability and safety. The bridge's deck is suspended from the towers using large-diameter steel cables. These cables are made from high-strength steel and are capable of bearing significant loads. The cables were fabricated in sections, then transported to the construction site, where they were then assembled and installed using specialized cranes and cable-spanning techniques.
The deck itself is composed of precast concrete segments, which were manufactured off-site and then transported and assembled on-site. The construction of the bridge's foundations involved significant geotechnical challenges. The foundations were constructed using large-diameter bored piles, which were drilled deep into the seabed to provide the necessary support for the bridge towers. The piles were reinforced with steel cages and filled with high-strength concrete to ensure their durability and load-bearing capacity. The construction process also included the installation of expansion joints and bearings to accommodate the bridge's movements due to thermal expansion, traffic loads, and seismic activity. The expansion joints are designed to allow for controlled movements of the bridge deck while maintaining a smooth and continuous driving surface. The Brasilia Digital TV Tower is a landmark structure in Brazil, designed by renowned architect Oscar Niemeyer. The tower stands at 600 feet tall and serves both as broadcast facilities and a tourist attraction. The construction of the tower involves advanced engineering techniques and careful architectural design to ensure its functionality and aesthetic appeal. The tower's foundation is a critical component, requiring deep piles driven into the ground to support the massive structure. These piles are typically made of reinforced concrete, providing the necessary strength and stability. The main structure is composed of a reinforced concrete core, surrounded by steel framework. This combination of materials ensures the tower is both strong and flexible, capable of withstanding wind loads and other environmental forces. One of the unique features of the Brasilia Digital TV Tower is its observation deck, located near the top of the structure. Constructing the deck involves installing large glass panels and steel supports to create a safe and accessible space for visitors. The deck provides panoramic views of the city, making it a popular tourist destination. The tower also houses advanced broadcasting equipment, including antennas and transmitters for digital TV signals. Installing this equipment requires precise engineering and coordination to ensure optimal signal strength and coverage. The equipment is housed in specially designed rooms within the tower, protected from environmental factors and easily accessible for maintenance. In addition to its technical functions, the Brasilia Digital TV Tower is an architectural masterpiece, embodying Niemeyer's vision of fluid organic forms. The construction process required collaboration between engineers and architects to ensure the structure's aesthetic integrity while meeting functional requirements. The tower's sleek modern design is a testament to Brazil's commitment to innovation and progress. It's time to talk about one of the most recognized landmarks in the world, the Sydney Harbour Bridge in Australia, completed in 1932. Spanning 1,650 feet across Sydney Harbour, this bridge connects the bustling central business district with the vibrant North Shore. Its design, characterized by a massive steel arch rising 440 feet above the harbour, earned it the nickname the Coat Hanger. The bridge's construction utilized 52,800 tons of steel, assembled using a technique that involved building the two halves of the arch simultaneously and then joining them in the center, a method requiring precise engineering and coordination. The construction was a colossal endeavor, involving over 1,400 workers at its peak. These workers faced perilous conditions, often working at dizzying heights without the safety standards that are common today. Despite these challenges, the project was completed on schedule, thanks to the rigorous planning and the application of cutting-edge engineering techniques of the era. The bridge's deck, supported by massive steel trusses, was designed to accommodate both vehicular and rail traffic, reflecting its essential role in Sydney's transportation network. One of the remarkable engineering achievements was the method used to erect the steel arch. Each half of the arch was built from pylons and gradually extended toward the center. When the two halves were complete, they were carefully aligned and connected, a process that required meticulous precision. And this method not only showcased the engineering capabilities of the time, but also highlighted the daring nature of the construction process. In addition to the arch, the Sydney Harbour Bridge features 4 large granite-faced pylons, which, although not structurally necessary, add to the bridge's aesthetic appeal. These pylons also house various facilities, including lookout points that offer panoramic views of the Sydney Harbour and the city skyline. But how about one of the busiest bridges in the world? Constructed between 1927 and 1931, the George Washington Bridge was designed by Swiss-American engineer Othmar Ammann, who utilized innovative techniques to create what was then the largest suspension bridge in the world. The bridge's main span, which measures 3,500 feet, was a record-breaking achievement at the time of its completion. The bridge's design includes two main cables, each 36.5 inches in diameter, made up of around 26,000 individual wires bound together. These cables were manufactured and spun on-site using the saddle method, which involved spinning the wires from one anchorage over the tower tops and down to the other anchorage. This method allowed for precise tensioning of the cables and was crucial for the bridge's structural integrity. The bridge's two towers, each standing 604 feet tall, are composed of steel and rest on massive concrete foundations anchored into the bedrock beneath the river. The towers were initially designed to be clad in granite, but due to the economic constraints of the Great Depression, they were left as exposed steel, which has become an iconic feature of the bridge. The open steel lattice structure of the towers not only provides the necessary strength, but also reduces wind resistance, which is vital for the stability of such a large suspension bridge. The construction of the bridge required significant feats of engineering and logistics. Workers built caissons on the riverbed to serve as foundations for the towers. They were sunk to depths of up to 80 feet below the water level and filled with concrete to provide a stable base for the towers. Building the caissons was one of the most challenging parts of the construction, requiring deep excavation and precise engineering to ensure stability. The bridge's deck was initially designed to carry 6 lanes of traffic, but due to the structure's robustness and foresight in design, a second deck was added in 1962, increasing the total capacity to 14 lanes. This lower deck, known as Martha, was added without interrupting the flow of traffic on the upper deck, a significant engineering accomplishment that showcased the bridge's adaptability and demands forward-thinking design. The George Washington Bridge was completed ahead of schedule and under budget, which is a testament to the efficiency and skill of Aman and his team. It opened to traffic on October 24, 19, and has since become a vital transportation link, handling more than 100 million vehicles annually. We have to travel over to Peru now, for the Chinchero International Airport construction project. Located near Cusco, it's a major infrastructure project designed to enhance the region's connectivity and support the growing tourism industry. Cusco is a gateway to Machu Picchu, one of the world's most popular tourist destinations, and the new airport aims to accommodate the increasing number of visitors while alleviating congestion at the existing Alejandro Velasco Este International Airport. Construction on the Chinchero International Airport began in 2018, with the project expected to be completed by 2025. The airport will feature a modern terminal building, a 13,000-foot runway, and state-of-the-art navigation and communication systems. The terminal will be designed to handle up to 5 million passengers annually, providing a significant boost to the region's tourism infrastructure. One of the key engineering challenges of the Chinchero International Airport project is its location at an altitude of approximately 12,500 feet above sea level. The high-altitude environment presents unique challenges for aircraft performance and passenger comfort, requiring specialized design and operational considerations. The project also involves extensive earthworks and site preparation to ensure the stability and safety of the project infrastructure. The total cost of the Chinchero International Airport project is estimated at $500 million, funded by the Peruvian government and international investors. The project is expected to generate a significant economic benefit, including job creation during the construction phase and increased tourism revenue once the airport is operational. It's time to travel over to the country of China. Here, the Shanghai-Nantong Yangtze River Bridge is a major infrastructure project designed to improve connectivity between Shanghai and Nantong. This $3.5 billion bridge spans 11 kilometers across the Yangtze River, making it one of the longest cable-stayed bridges in the world. Construction of the bridge began in 2014, with the project completed in 2020. One of the primary engineering challenges was constructing a bridge that would accommodate both road and rail traffic. The bridge features a dual-use design, with a 6-lane highway on the upper deck and a 4-track railway on the lower deck. This design requires advanced engineering techniques to ensure the bridge's stability and load-bearing capacity. The bridge's main span is 1,092 meters long, supported by 2 towers that reach a height of 325 meters. These towers are among the tallest bridge towers in the world, requiring precise engineering and construction techniques. The towers are constructed using high-strength concrete and reinforced steel to withstand the heavy loads and environmental conditions of the Yangtze River.
One of the key innovations in constructing the Shanghai-Nantong Yangtze River Bridge is the use of large-diameter steel cables to support the bridge deck. These cables are made from high-strength steel and can bear the significant weight of the combined road and rail traffic. The cables are anchored in massive concrete blocks on either side of the river, providing the necessary tension to support the bridge deck. The construction of the bridge also involved extensive foundation work, using deep-water drilling techniques to create stable foundations in the riverbed. These foundations are designed to resist the strong currents and seismic activity of the region, ensuring the long-term stability and safety of the bridge. Engineers employed advanced geotechnical analysis and testing to ensure the foundations could withstand the dynamic forces exerted by the river and passing trains. The Napoli-Afragola rail station in Italy is a modern transportation hub designed to improve connectivity between Naples and other major Italian cities. The station, designed by architect Zaha Hadid, features a striking architectural design and advanced construction techniques. The station includes multiple levels, extensive platforms, and state-of-the-art passenger facilities. The construction of the station involves extensive earthworks, concrete pouring, and steel reinforcements to create a stable and durable structure. The platforms are designed to accommodate high-speed trains, requiring precise alignment and smooth surfaces to ensure safe and efficient operations. Engineers use advanced surveying and construction techniques to achieve the necessary precision. One of the significant challenges of the Napoli-Afragola rail station project is integrating the new station with existing rail infrastructure. This involves constructing new rail lines, switches, and signaling systems to ensure seamless connections with the existing network. Engineers use advanced computer modeling and simulation tools to plan and optimize the rail connections, minimizing disruptions to existing services. Additionally, the station's design incorporates numerous sustainability features, such as natural lighting, energy-efficient systems, and green spaces. These elements reduce the station's environmental impact and enhance passenger comfort. The station's construction also requires meticulous planning to preserve the surrounding landscape and minimize disruption to local communities. Located in Louisiana, the Lake Pontchartrain Causeway stands as a monumental testament to bridge engineering. Stretching a staggering 24 miles across the Lake Pontchartrain, this bridge holds the title of the longest continuous bridge over water in the world. The construction of the causeway began in 1955 and was completed in 1956, with a parallel span added in 1969 to accommodate the growing traffic. The project required the installation of over 9,000 concrete pilings, each driven deep into the lake bed to ensure stability and resilience against the water's varying conditions. The engineering marvel connects the cities of Metairie and Mandeville, significantly enhancing regional connectivity and economic integration. The causeway's design and construction addressed numerous challenges, including the lake's depth and the need for a structure that could withstand the harsh environmental conditions. The bridge's sheer length necessitated the use of innovative construction techniques and materials to ensure its longevity and safety. It features a series of low-rise spans supported by concrete pilings, creating a durable and stable roadway that has stood the test of time. The Lake Pontchartrain Causeway not only facilitates the daily commutes of thousands of residents, but also plays a crucial role in emergency evacuations during hurricanes, highlighting its strategic importance. In terms of economic impact, the causeway has significantly boosted local businesses by improving access to the greater New Orleans area. It also has become a vital route for freight transport, supporting the movement of goods across the region. The bridge's maintenance and operational management continue to be a priority, with regular inspections and upgrades to ensure its structural integrity. It's time to move over to Colombia next for the Orient Tunnel project, designed to improve connectivity between Medellin and Jose Maria Cordova International Airport in Rio Negro. This road tunnel is the longest in Colombia, spanning approximately 5.7 miles. Construction of the Tunnel de Orient began in 2012 and was completed in 2019. The project involved extensive geological surveys and the use of advanced tunneling techniques to navigate the complex terrain of the Andes Mountains. The tunnel features dual bores, each accommodating 2 lanes of traffic, ensuring a smooth flow of vehicles and enhancing safety. One of the key benefits of the Tunnel de Orient is the reduction in travel time. Prior to the tunnel's construction, the journey between Medellin and the airport took approximately 45 minutes to an hour, depending on traffic conditions.
The tunnel reduces this travel time to just 18 minutes, providing a more direct and efficient route. The total cost of the Tunnel de Orient project was approximately $300 million, funded by a combination of public and private investments. The project has generated significant economic benefits, including job creation during the construction phase and increased commercial activities once the tunnel became operational. Environmental and social considerations were integral to the project. Comprehensive environmental impact assessments were conducted to minimize the impact on local ecosystems and communities. The project also included measures to manage water resources, protect wildlife, and engage with local stakeholders to ensure that the benefits of the tunnel are shared with the surrounding areas. Next up, we have to move over to Japan for the Azabudai Hills project, located in Tokyo. The project, costing approximately $5.5 billion, covers an area of 8.1 hectares and includes 3 skyscrapers, green spaces, and public facilities. Construction of Azabudai Hills began in 2019, with the project expected to be completed by the end of 2024. One of the primary challenges in this project is the dense urban environment in which it is being built. To minimize disruption to the surrounding area, construction is being carried out in phases, with careful planning and coordination to ensure safety and efficiency. The project features 3 high-rise buildings with the tallest reaching a height of 330 meters. These buildings will house offices, apartments, hotels, and retail spaces, creating a vibrant mixed-use environment. A key innovation in the Azabudai Hills project is the integration of green spaces and public facilities within the urban environment. The development includes a central park which covers approximately 24,000 square meters and provides a green oasis in the heart of the city. The project also incorporates state-of-the-art sustainability features such as energy-efficient building systems, renewable energy sources, and advanced waste management systems. One of the significant engineering challenges in the Azabudai Hills project is the construction of the underground infrastructure. This includes the creation of underground parking facilities, utility tunnels, and pedestrian networks that connects the various buildings and public spaces. Advanced tunneling and excavation techniques are used to ensure the stability and safety of the underground structures, while minimizing the impact of the surrounding environment. In addition to its architectural and environmental features, Azabudai Hills aims to create a sense of community and connectivity within the urban environment. The development includes a range of public amenities such as schools, healthcare facilities, and community centers, which are designed to meet the needs of residents. Hyperloop One is a groundbreaking transportation project set to revolutionize travel. Conceptualized by Elon Musk and currently under development by Virgin Hyperloop, this project aims to create a high-speed transit system using pods traveling through low-pressure tubes. The technology relies on magnetic levitation to eliminate friction and achieve speeds exceeding 600 miles per hour. Construction involves several critical components: the tube system, the pods, and the stations. The tubes are constructed from steel and reinforced concrete, designed to withstand external pressures and natural disasters. One of the engineering challenges is maintaining a near-vacuum environment inside the tubes to maintain air resistance. This requires advanced sealing techniques and constant monitoring to ensure the integrity of the system. The pods themselves are made from lightweight durable material like carbon fiber and aluminum. They feature aerodynamic designs to reduce drag and increase efficiency. Inside, the pods are equipped with comfortable seating, safety systems, and climate control to ensure a pleasant travel experience. Each pod is designed to be autonomous, with advanced navigation systems to manage speed, direction, and braking. Construction of Hyperloop One includes the development of extensive infrastructure, such as the power supply systems, control centers, and emergency response facilities. The power supply for the Hyperloop is primarily derived from renewable energy sources like solar panels installed along the tube's length. Control centers are crucial for managing the network, monitoring pod positions, tube pressure, and overall system health. In cases of emergencies, the infrastructure includes rapid response teams and safety protocols to ensure passenger safety. One of the major construction challenges is the alignment and leveling of the tubes over long distances. Engineers use GPS technology and laser alignment systems to ensure the tubes are perfectly straight and level. This precision is essential to maintain the high speeds and safety standards of the Hyperloop. Additionally, constructing the system in various terrains, from urban environments to open countryside, requires adaptable construction techniques and materials.
We have to talk about the 1915 Canakkale Bridge next, which is located in Turkey. Spanning the Dardanelles Strait, this suspension bridge connects the towns of Galibalu on the European side with Lapseki on the Asian side. With a main span of 6,637 feet, it is the longest suspension bridge in the world, surpassing Japan's Akashi Keikyo Bridge. The construction of the 1915 Canakkale Bridge was a monumental task that involved overcoming numerous engineering challenges. The project, which cost approximately 2.8 billion euros, employed thousands of workers and utilized state-of-the-art technology and materials. The bridge's design includes two massive towers, each standing 1,043 feet tall, constructed using high-strength steel. These towers support the main cables, which are composed of over 162,000 miles of steel wire, meticulously spun on site to ensure optimal tension and load distribution. One of the key challenges was constructing the bridge in a seismically active area. To address this, engineers incorporated advanced seismic protection measures, including special bearings and dampers that allow the bridge to absorb and dissipate seismic energy. These features are crucial for ensuring the bridge's stability and safety in the event of an earthquake. Additionally, the bridge is designed to withstand the strong winds and harsh environmental conditions typical of the Dardanelles Strait. The bridge deck, which carries 6 lanes of traffic, was constructed using prefabricated sections. These sections, each weighing several hundred tons, were transported to the site by barges and lifted into place using specialized cranes. This method allowed for precise alignment and efficient assembly of the bridge deck, minimizing construction time and ensuring high-quality craftsmanship. Next, we have to move over to Chile, where the Solar Program project is an ambitious initiative to harness the country's abundant solar energy potential. The program includes several large-scale power projects with a combined capacity of over 2,000 megawatts, making Chile one of the leading solar power producers in Latin America. One of the flagship projects under the Chile Solar Program is the Atacama Solar Plant, located in Atacama Desert, which is known for its high solar irradiance. The plant has a capacity of 246 megawatts and features over 776,000 panels spread across 1,000 hectares. The Atacama Solar Plant is capable of generating enough electricity to power approximately 200,000 homes. Construction of the Atacama Solar Power Plant began in 2014 and was completed in 2016. The project involved extensive planning and engineering to ensure the efficient capture and conversion of solar energy. Advanced photovoltaic technology was used to maximize energy output, and the plant's design includes features such as the single-axis tracking system that allows the sun's movements to optimize panel orientation. The Chile Solar Program also includes the development of the El Romero Solar Plant, which has a capacity of 246 megawatts and is one of the largest solar plants in Latin America. Located in the Vallenar region, the plant covers an area of 280 hectares and features over 800,000 solar panels. The total investment in the Chile Solar Program is estimated at $4 billion. The program has generated significant economic benefits, including job creation and increased investment in the renewable energy sector. The development of solar energy projects also contributed to the diversification of Chile's energy mix, reducing reliance on fossil fuels and enhancing energy security. It's time to travel over to the United States for the Gilmerton Bridge Replacement Mega Project. The new bridge, costing approximately $134 million, aims to improve traffic flow and safety for the thousands of vehicles and vessels that pass through this corridor daily. Construction of the Gilmerton Bridge replacement began in 2009, with the new bridge opening to traffic in 2013. The new bridge is a vertical lift bridge, which provides several advantages over the old bascule bridge. The vertical lift design allows for a higher clearance from maritime traffic, reducing the number of bridge openings and minimizing delays for both road and river traffic. The new bridge features a vertical clearance of 35 feet when closed and up to 135 feet when fully lifted, accommodating larger vessels that navigate the river. The construction of the bridge includes several advanced engineering techniques. The bridge's foundations were constructed using drilled shafts, which provide greater stability and load-bearing capacity compared to traditional pile foundations. These shafts were drilled deep into the riverbed, and the bridge could support the heavy traffic loads and withstand the harsh environmental conditions of the river. One of the key innovations in the Gilmerton Bridge Replacement Project was the use of precast concrete segments for the bridge's superstructure. These segments were manufactured off-site and transported to the construction site, where they were assembled using a balanced cantilever method. The project also included significant upgrades to the bridge's mechanical and electrical systems. The new bridge is equipped with state-of-the-art lifting machinery and control systems, ensuring reliable and efficient operation. The project included the construction of new pedestrian and bicycle pathways, enhancing accessibility and promoting alternative methods of transportation. Batam Bam Port in Indonesia is a significant infrastructure project aimed at enhancing the country's maritime trade capacity. Located in West Java, the port includes a container terminal, car terminal, and supporting infrastructure. The construction of Batam Bam Port involves a land reclamation, dredging, and construction of extensive port facilities. Land reclamation is the first step, involving the creation of new land by dredging and filling the seabed with sand and rock. This process requires precise engineering to ensure the reclaimed land is stable and suitable for construction. Engineers use advanced geotechnical techniques to compact and reinforce the soil, preventing subsidence and ensuring long-term stability. Dredging is essential for creating deep water channels and berths to accommodate large vessels. This involves removing sediment and rock from the seabed using specialized dredging equipment. The dredged material is carefully managed to minimize environmental impact, and in some cases, it is used for land reclamation. The construction of port facilities includes building quays, warehouses, and support infrastructure. The quays are constructed using reinforced concrete piles, driven deep into the seabed to provide a stable foundation. On top of these piles, concrete decks are cast to create the surface where cargo operations take place. Warehouses and other buildings are constructed using steel frames and prefabricated panels, allowing for rapid assembly and scalability. One of the significant challenges of the Batam Bam Port project is managing the environmental impact of dredging and land reclamation. Engineers work closely with environmental experts to implement mitigation measures, such as creating artificial reefs and mangrove restoration projects to preserve marine habitats. Additionally, the project must adhere to strict safety and operational standards to ensure the ports can handle the anticipated increase in maritime traffic. Moreover, the integration of advanced port management systems is crucial for optimizing cargo handling and logistics. These systems include automated cranes, real-time tracking, and inventory management tools to ensure efficient and timely operations. The port's strategic location and state-of-the-art facilities are expected to enhance Indonesia's role in global trade. It's time to talk about the Rio Antirio Bridge in Greece, officially known as the Charalaos-Trikopis Bridge. Completed in 2004, this cable-stayed bridge spans nearly 1.8 miles across the Gulf of Corinth, making it one of the longest multi-span cable-stayed bridges in the world. The bridge significantly improves connectivity and travel efficiency in the region, which previously relied on ferry services. Constructing the Rio Antirio Bridge presented numerous engineering challenges, primarily due to the deep waters, strong seismic activity, and high winds in the Gulf of Corinth. The bridge's foundations were a critical aspect of the project, designed to withstand these harsh conditions. Each of the four main pylons is anchored to the seabed using a combination of gravity caissons and driven piles. These caissons were filled with concrete and gravel, providing a stable and resilient foundation capable of withstanding seismic forces and soil liquefaction. The bridge's pylons, rising 492 feet above the water, were constructed using high-strength concrete and designed to be flexible enough to absorb seismic shocks. This flexibility is essential in an earthquake-prone area, allowing the bridge to move slightly with the seismic waves, rather than resisting them rigidly, which would risk structural damage. Additionally, the pylons are equipped with hydraulic dampers to further mitigate seismic impacts. The main span of the bridge is supported by 368 cables, arranged in a fan-like pattern that distributes the weight to the bridge deck evenly. These cables are made of high-tensile steel and were carefully tensioned to ensure optimal load distribution. The bridge deck itself is constructed from pre-stressed concrete segments, which were cast on shore and then transported to the site for installation. This method allowed for high precision and quality control during construction. The Rio Antirio Bridge also incorporates an innovative expansion joint system that accommodates thermal expansion and contraction, ensuring the bridge remains stable and functional across a range of temperatures.
This system is crucial for maintaining the bridge's integrity over its lifespan, particularly in a region with significant temperature variations. But what about a country that got a brand new metro system? That's what happened with the Metro de Quito project. The metro line spans approximately 14 miles and includes 15 stations, connecting the southern and northern ports of Quito. Construction of the Metro de Quito began in 2013, and the project faced numerous challenges, including the city's complex geology and the need to preserve historical sites. The metro tunnels were excavated using tunnel boring machines, which allowed for precise and efficient tunneling while minimizing surface disruptions. The use of the machines also ensured the protection of Quito's colonial-era buildings and historical landmarks. The Metro de Quito is designed to accommodate over 400,000 passengers daily, significantly reducing the number of vehicles on the road and improving air quality. The metro system features modern trains equipped with the latest technology, including automated systems for safety and efficiency. The stations are designed to be accessible and user-friendly, with features such as elevators, escalators, and clear signage. One of the significant benefits of the Metro de Quito is the reduction in travel time. Commuters can travel from one end of the city to another in approximately 34 minutes, compared to over an hour by car during peak traffic. This improvement in mobility is expected to boost economic activities and enhance the quality of life for Quito's residents. The total cost of the Metro de Quito project is estimated at $2 billion, funded by a combination of national and international sources. The project has generated significant economic benefits, including job creation during the construction phase and increased commercial activities around the metro stations. Environmental sustainability is a key aspect of the Metro de Quito project. The metro system is powered by electricity, reducing greenhouse gas emissions and contributing to Quito's efforts to combat climate change. The project also includes measures to manage noise and vibration, ensuring minimal disruptions to the surrounding communities. Let's move over to Egypt now, where the Grand Egyptian Museum is being constructed. Located near the pyramids of Giza, this $1 billion project covers approximately 120 acres and showcases Egypt's rich cultural heritage through state-of-the-art exhibits and facilities. One of the primary engineering challenges was creating a stable foundation for the massive structure, given the proximity to the pyramids and the potential for archaeological discoveries during excavation. Engineers employed advanced ground-penetrating radar and other non-invasive techniques to survey the site before construction, ensuring that any significant archaeological finds could be documented and preserved. The construction of the Grand Egyptian Museum involved several advanced engineering techniques. The building's foundations required deep excavation and the use of high-strength concrete to support the massive weight of the structure. To address the region's seismic activity, engineers incorporated earthquake-resistant features, such as base isolators and flexible joints, into the design. These features help absorb and dissipate seismic energy, protecting the structure from potential damage during an earthquake. One of the most striking features of the museum is the massive 82-ton statue of Ramses II, which stands in the entrance atrium. Engineers used a specially designed gantry crane and sophisticated system of rollers and supports to transport and position the statue without causing any damage. The sheer size of the project required the coordination of thousands of workers and the management of vast amounts of materials. Engineers employ advanced project management software to monitor progress, allocate resources, and address any issue that arose during construction. The Incheon International Airport expansion in South Korea is a massive project aimed at increasing the airport's capacity and improving passenger services. The expansion includes the construction of a new terminal, additional runways, and supporting infrastructure. The new terminal, Terminal 2, is designed to handle 18 million passengers annually, increasing the airport's total capacity to 72 million passengers. Constructing the new terminal involves extensive earthworks, concrete pouring, and steel erection. The terminal is designed with a modern, open layout featuring large glass windows and high ceilings to create a spacious and welcoming environment. Advanced construction techniques, such as prefabrication and modular construction, are used to speed up the building process and ensure high-quality finishes. The expansion also includes the construction of new runways, which involves extensive earthworks, grading, and paving. The runways are designed to accommodate the largest commercial aircraft, requiring precise engineering to ensure smooth and safe landings and takeoffs. One of the significant challenges of the Incheon International Airport expansion is managing construction activities while keeping the airport operational. Engineers and planners must carefully coordinate construction schedules and activities to minimize disruptions to airport operations and ensure the safety of passengers and workers. Additionally, the expansion incorporates numerous sustainability features such as energy-efficient systems, green roofs, and rainwater harvesting. These elements reduce the environmental impact of the airport and enhance passenger comfort. The construction also involves extensive collaboration with local authorities and communities to address concerns and ensure compliance with regulations. It's time to investigate the Sidu River Bridge, located in China. This suspension bridge spans an incredible 4,000 feet and is one of the highest bridges in the world, with a deck that towers 1,627 feet above the river below. The bridge connects the cities of Yesengguan and Dazeping, dramatically improving transportation across the mountainous region. The construction of the Sidu River Bridge was a formidable challenge due to the extreme heights and the rugged terrain. The project involved over 2,000 workers who utilized advanced engineering techniques and faced considerable risks to complete the bridge. The bridge's main cables, each made up of 127 high-strength steel wires, were installed using a novel method that involved rocket technology to stretch the pilot lines across the vast gorge. This innovative approach allowed for precise placement and tensioning of the cables, ensuring the bridge's stability and structural integrity. One of the critical engineering achievements was the construction of the bridge's massive towers, which rise 295 feet above the bridge deck. These towers were built using reinforced concrete and were designed to withstand significant seismic activity, given the region's susceptibility to earthquakes. The bridge deck, constructed using lightweight yet strong materials, is designed to handle both vehicular and pedestrian traffic. The deck's aerodynamic design helps to reduce wind resistance and ensure stability during high winds, which are common in the mountainous area. The construction team also implemented a comprehensive monitoring system to continuously assess the bridge's structural health and detect any potential issues in real time, ensuring long-term safety and reliability. The Sidu River Bridge has significantly reduced travel times between the two cities it connects, fostering economic growth and development in the region. We travel over to Chile next, where the Chacao Channel Bridge is located. This project, once completed, will significantly improve transportation and economic integration between the island and the mainland. Construction on the Chacao Bridge began in 2018, and the project is expected to be completed by 2025. The bridge will span approximately 1.7 miles across the Chacao Channel, featuring a central suspension span of 3,350 feet, making it one of the longest suspension bridges in the world. The bridge will have two main pylons, each rising about 656 feet above the water, supporting the central span with massive steel cables. One of the critical challenges of the Chacao Channel Bridge project is the harsh environmental conditions of the Chacao Channel. The area is known for strong winds, powerful tides, and seismic activity, all of which pose significant engineering challenges. The bridge is designed to withstand these conditions, incorporating advanced materials and construction techniques to ensure its durability and safety. The bridge will accommodate both vehicular and pedestrian traffic, with 2 lanes in each direction and dedicated pathways for pedestrians and cyclists. This infrastructure will replace the current ferry system, which is often subject to delays and weather-related disruptions, providing a more reliable and more efficient transportation link. The project is estimated to cost around $740 million, with funding sourced from both the Chilean government and international investors. The economic benefits of the bridge are expected to be substantial, including increased tourism, reduced transportation costs, and enhanced economic integration between Chiloé Island and the mainland. Next on our list is the Vasco da Gama Bridge in Portugal. Spanning an impressive 10 miles, this bridge is the longest in Europe, connecting the northern and southern parts of Lisbon across the Tagus River. Completed in 1998, the Vasco da Gama Bridge was constructed to alleviate the traffic congestion on the 25 de Abro Bridge and to support the growing urban sprawl. The project cost approximately $1 billion, reflecting its vast scale and the advanced engineering techniques required for its completion. The construction of the Vasco da Gama Bridge was a monumental task, involving over 3,000 workers at its peak. The bridge's design includes several key features to ensure stability and longevity, particularly its resistance to seismic activity. Given Lisbon's history with earthquakes, special care was taken to incorporate flexible expansion joints and robust pylons that can withstand significant ground movement. The central span of the bridge is supported by cable-stayed structures with towers reaching up to 492 feet high, providing the necessary clearance for maritime traffic below. One of the most challenging aspects of the construction was dealing with varying depths and tidal conditions of the Tagus River. The bridge's foundations are anchored deep into the riverbed, using steel and concrete piles, some of which extend more than 300 feet below the surface. This method ensures that the structure remains stable despite the dynamic water conditions. Additionally, the bridge features a series of viaducts and causeways designed to blend seamlessly into the surrounding landscape, minimizing the environmental impact. The bridge significantly reduces travel time between northern and southern regions of the country, facilitating commerce and daily commutes for thousands of residents.
The Red Line Doha Tunnel in Qatar is a key component of the Doha Metro network, designed to provide efficient and reliable public transportation. The construction of this 25-mile-long tunnel, completed in 2019, involved several engineering and logistical challenges, particularly given the region's geological conditions. The tunnel was constructed using tunnel boring machines, which are highly specialized for excavating through the soft rock and soil conditions prevalent in Doha. Each TBM was over 328 feet long and weighed approximately 1,200 tons. These machines were equipped with rotating cutter heads that excavated the soil and rock, which was then transported out of the tunnel using conveyor belts. The construction also involved the careful monitoring and management of ground settlement, particularly in urban areas. Advanced geotechnical instruments such as inclinometers and extensometers were installed to monitor ground movements and ensure the tunnel's stability. This real-time data allowed engineers to adjust construction methods and implement corrective measures as needed, minimizing the impact on existing buildings and infrastructure. The Red Line Doha Tunnel features a dual-track system, allowing for high-frequency train services. The tunnel is equipped with state-of-the-art systems for ventilation, lighting, and emergency evacuation. The ventilation system is designed to maintain air quality and manage smoke in the event of a fire, ensuring passenger safety. The construction process also included the development of underground stations, which required extensive excavation and support systems. These stations were designed with large open spaces to accommodate passenger flow and provide a comfortable environment. The use of advanced structural engineering techniques, such as diaphragm walls and deep foundation piles, ensured the stability and durability of these underground structures. The Red Line Doha Tunnel project showcases the application of advanced tunneling technology and engineering practices to create a modern, efficient, and resilient public transportation system. The project addresses the growing demand for sustainable transportation solutions in Doha, providing a reliable and high-capacity metro network that supports the city's development and connectivity. The Hisingsbron Bridge in Gothenburg, Sweden, a vertical lift bridge, is a remarkable engineering project aimed at replacing the aging Godalv Bridge. Scheduled for completion in 2021, the Hisingsbron Bridge stands out for its innovative design and construction techniques. The bridge spans approximately 1,300 feet and features a vertical lift mechanism, allowing it to accommodate both road and maritime traffic efficiently. The construction began with the installation of deep foundation piles, driven into the riverbed to provide a stable base for the bridge piers. These piles were made of high-strength steel and concrete, capable of withstanding the dynamic loads from both the bridge structure and passing ships. This foundation work required precise geotechnical surveys and advanced piling techniques to ensure the stability and longevity of the structure. The bridge's main span is constructed using steel box girders, which are prefabricated off-site and transported to the construction site. These girders were then lifted into place using heavy lift cranes and connected to the piers. The use of prefabrication allowed for high-quality control and reduced on-site construction time. Each girder segment was meticulously aligned and welded to form a continuous structure, ensuring the bridge's strength and durability. One of the unique features of the Hisingsbron Bridge is its vertical lift mechanism, which allows the central span to be raised to a height of 150 feet, providing clearance for maritime traffic. The lifting system consists of counterweights and powerful electric motors designed to operate smoothly and reliably. The bridge's control system includes advanced sensor and automation technology, allowing for precise and efficient operation. The construction also included the development of approach ramps and road connections, integrating the bridge into Gothenburg's existing transportation network. This required extensive earthworks and the construction of retaining walls and embankments to support the elevated roadways. The approach ramps were designed to provide smooth transitions and minimize disruptions to traffic flow. The Dig-Indi Tunnel System in Indianapolis, United States, is an extensive network of deep rock tunnels designed to reduce sewer overflows into local waterways. Scheduled for completion in 2025, this project involves the construction of over 28 miles of tunnels, each approximately 18 feet in diameter and located 250 feet below ground. The construction process began with the excavation of deep access shafts, providing entry points for tunnel boring machines. These TBMs were specially designed to excavate through the limestone bedrock prevalent in the region. The TBMs, each over 300 feet long, used rotating cutter heads to grind through the rock, creating the tunnel bore. The excavated material was transported out of the tunnel using conveyor belts and hoisted to the surface through the access shafts. The tunnel lining was constructed using precast concrete segments, which were installed by the TBMs as they advanced. These segments, designed to withstand the high pressures at depth, were bolted together to form a watertight lining. The use of precast segments allowed for rapid construction and high-quality control, ensuring the structural integrity of the tunnels. One of the primary engineering challenges was managing groundwater infiltration. The tunnels were designed with a comprehensive dewatering system, including pumps and drainage galleries to control groundwater levels and prevent flooding. Additionally, the tunnel lining included waterproof gaskets and grout injection systems to seal any potential leaks. The Dig-Indi tunnel system also involved the construction of a large storage and conveyance structures designed to hold and transport combined sewer overflows during heavy rainfall events. These structures were integrated with the existing sewer network, requiring extensive coordination and planning. The project included the installation of advanced control systems, allowing for real-time monitoring and management of these sewer flows. The Dig-Indi Tunnel System project showcases the application of advanced tunneling technology and engineering practices to address critical infrastructure needs. The project significantly reduces sewer overflows, improving water quality and public health in Indianapolis. The construction of this extensive tunnel network demonstrates the capabilities of modern engineering to solve complex urban infrastructure challenges.